pretend that this is an ice cream. You want to be as close to it as possible.
Ice cream. Yes. Okay. Yeah. Okay. Testing. Testing. Hello.
the song.
change the status? Yeah, okay.
Doesn't look like.
Test. Aye, perfect.
Okay, that should work. Good.
Works? Yes, that works. So you said it's like an ice cream. Okay, it's like an ice cream. All right. So welcome to this 8th workshop on type-driven development called pronounced TyDe. And so to illustrate this, I took a picture of my daughter's bedroom because it was not tidy. So we're the tidying experts here, and I use it as a kind of trigger, right? So you go by the corridor and you see this picture. It's like a Python program that just needs structure. So that's why I did this. So we have a great menu this year. We have today we'll have 5 full papers. So that's these 12 pages research papers that I think you can already find them on the ACM digital library. And then there are also 7 extended abstracts, so up to 3 pages, and they are posted on the workshop webpage, so you can read them straight away. And it covers a very broad range of topics, which we kind of try to, pack them up. It's not really natural, but essentially there is one session this morning which is on types for types, type-driven types. So you will see inference rules for this morning to just kind of warming up. And then there will be a second session, which is type-driven designs, when you want to design software and you use types to help you there. And the first session, which is very close to my heart, is what do you do when you want to get types to be there at runtime? So dependent types and other things like this. Okay, so so that's the plan for today, and I think it will cut quite nice. We had a lot of fun reading the papers. So I would like to start with thanking the contributors. Everyone who submitted a paper to TyDe. It was very nice. A lot of very well written papers. We had a lot of pleasure reading them as in the program committee. You can find the list of the program committee members online. Well, all very good discussions. It was very interesting to be there and to try to drive decisions there. And we did something which was to enlist external reviewers. So I should personally thank them for doing the work, because they did not appear on the program committee, but still they did a few reviews. So Emilio Gallego, Soichiro Fuji, Michael Laurent, Loïc Perrault, and Frédéric Peshansky, as well as Louis Chang. They all pitched in, bringing their expert point of view on some papers. So it was quite interesting to get this narrow focus view on some papers. I should also thank the TyDe steering committee, which was wonderful, and the organizer of ICFP, and especially the workshop chairs, Arthur, Yannick. We saw them roam around because they do all the work, so that I don't have to do any work. So and thank you as well. So I'm very happy not to have to do the YouTube shebang and all that. So thank you for doing this. So we are live on YouTube right now. I mean, my voice is live, my face is not, which I guess is pretty good. And so that's thanks to this wonderful organization. Okay, and let's not forget, so I'm just one PC chair. I'm a co-PC chair, so that means I'm a PC chair in the dual category of workshop. And so let's not forget about Yu Kang, who could not be there today for visa issues and travel was a bit complicated, but she was absolutely wonderful. So she's my categorical dual, right? So when I'm administratively lazy, she is administratively very efficient. So that's why there is a workshop today, because she replied to these emails that I thought, oh man. So she has been wonderful. Okay, that's it for the thanks and for the acknowledgements. And now we have to start the day, and we're starting the day with a keynote. That was also hard work to get you there, but we managed. And so we have Jeremy Gibbons today from Oxford University giving us a keynote on generative programming. Who is Jeremy? Everyone knows Jeremy. Jeremy is on Wikipedia, right? So you know who is Jeremy. Perhaps I should still do my homework. So At University of Oxford, Jeremy is a professor of computing, and he leads the algebra programming team. And it's no small thing, right? Algebra programming is really, that's very the jewel of this, right? It's very TyDe in the spirit. It's trying to use often the categorical language to kind of structure what the kind of programs we write and try to understand for algorithms, for programs, what's the underlying mathematical structure. And so Jeremy is carrying this work, and in parts as part of, for example, the ICFP working group 2.1, which is kind of a group that carries the flame of the squiggles, right? Among many other things, but that's still a place that where this lives and this carry on this work. And also as well in the working group 2.11 on program generation. So we know Jeremy for his work on functional programming, his patterns in programming. We also know him for these emails we sometimes received from the Journal of Functional Programming, where he was editor-in-chief. He was very kindly asking you, could you review this thing? He was also the guardian of the pearls, the functional pearls, right? So this torch has moved on, right? But you should still submit to JFP, and now it's open access, so you have no excuse, I'm told. And now Jeremy is still editor-in-chief of a programming journal, again very TyDe, and the open access journal called Compositionality. So all good reasons to keep sending love letters to Jeremy, as I'm doing right now, through papers. All right, so without much ado, please welcome Jeremy.
Thank you, Pierre, for the very kind words. Is the mic on? Yes, do send me love letters. So, with apologies to those who are on YouTube and don't have a view, I'm wearing this T-shirt, which is a souvenir from ICFP in 2017, which is just helpers, and it's got a little monadic program on the back for what student helpers do. And I didn't think this through, so I was having a chat outside with a colleague, and some poor lost student came up to me and said, "Where do I go?" Yeah, so maybe I should have been a bit more circumspect. I'm going to talk about joint work with my co-authors are credited at the end, Tom Shrivers, Nick Wu, and Ashin Kidney. This is a paper we had at the Maths to Program Construction conference last year, which is another very TyDe place, and but it's a conference that happens quite rarely. It's sort of every 3 or 4 years. If you spot it, you should submit something to it. And I suppose without further ado, let me get into it. I'm not sure we're going to get the bottoms of all the slides. Well, anything missing. It's about applicative functors, which I'm guessing you're all familiar with, but they're a bit like monads. They're a way of capturing effectful computation in a pure language. They're a simpler version of monads in the sense that they're less powerful than monads, which means there's more of them than there are monads. So every monad is one of these applicative functors, so states and I/O and all these things. But a few other things are applicative as well. And I'm not going to get into the differences between monads and applicatives, just to say this is about applicatives in the sense that we don't need the extra power that monads provide to tell this story, that we can still exploit it if that extra power happens to be there. And it's I'm going to construct an applicative functor, and I'm not going to do the extra mile to construct a monad, which will be harder work because it's a stronger property, and I can't, I think, construct the monad for this. So the applicative functors are the sweet spot here. This idea of applicative functors was popularized by Conor McBride and Ross Patterson in a lovely functional Perl. And with some misgivings, I'm going to diverge from their notation. So they're in the Haskell library, they're sort of core Haskell programming style these days, and the Haskell library interface is not the one I'm going to use. No, so the Haskell library interface is the lower one, I'm going to use the upper one. Connor and Ross were exactly right that the Haskell interface is the one you want for programming with. It's the more convenient interface for programming with. But it's the less convenient one for thinking about the theory of and the implementation of one of these applicative functors, I think. And I'm going to use this different but equivalent interface at the top. In the same way, you may be aware that there's two ways of looking at monad, at least two ways of looking at monads. So there's the Haskell way with return and bind, which is convenient and is the language of do notation, which is on the back of my t-shirt. But completely alien well, not completely alien, but not the natural mathematical construction to category theorists. There's the joke about monads are just monoids in the category of endofunctors. Where's the monoid in return and bind? That's not clear at all. But there's the sort of natural categorical presentation makes the monadic structure clear. So if you're familiar with that difference with monads, it's the same kind of thing going on here. Applicative functors, what you need to be able to do is make a neutral computation. So think of this little f as being a type of computations. It's a parameterized type. So f of int is computations that might have some effects and return an int. There's a skip computation that returns void. The unit type returns no effects. And there's a kind of sequential composition. So if you've got a computation that can return A's and another computation that can return B's, then you can run the first one, run the second one, and you'll get an A and a B as a result. So this is a kind of unit thing, and this is a kind of pairing thing, and you see that you're going to get monoidal kinds of things out of that, and the laws that you have to satisfy to be an applicative functor are monoidal laws for this structure. So the categorical slogan is that they are strong lax-monoidal functors. That better? Or you better? Good. So if it's just on one, it might slide round. Let's see how. So, and then a thing that's in Connor and Waters' lovely paper, it's a short paper with all sorts of riches in it, is this idea of applicative traversal of a data structure. So a data structure is here T, it's another parameterized type, so think trees, but with they're polymorphic types. So there's trees of A's, trees of B's, and so on. And if you have an effectful function that you can do for each element, so you can turn A's into B's but have some effects of class F, then you can traverse your entire tree of A's and turn it into a tree of B's, collecting some effects as you go. So you might do some I/O at every element of the tree, or you might use some mutable state for every element of the tree. Again, with some laws, and I did some work on this, and some other people tidied it up and did it better. Mario Yaskeliov, Andrei Ripacek, Ezekiel Rivas have given a better presentation of it, so that's the one you should read. So there are three laws that say this is a well-behaved notion of traversal over a data structure. So basically you have to visit every element precisely once. Not saying anything about what order, so you could visit a list from left to right or from right to left. You could visit a tree in depth first order or in order breadth first, whatever. Those are all well behaved, but you have to visit everything precisely once. And there's some naturality properties about the effects as well. And again, I'm not going to get into those. They will be used, but I'll just tread lightly over them. So for example, this is the way to traverse lists. In Haskell, I should have written this with square brackets. Lists are traversable, and this is how you do traverse. if you're trying to visit every the empty on, so it could be just skip. So here I'm doing it in the Haskell presentation, so this is like return the empty list without doing any effects, because there are no elements to visit, so you don't use your effectful traversal body at all. And then for a non-empty list, xcons x's, this is where Connor's clever notation works beautifully. This is a kind of funny application, and it's left associating like function application is. So there's parentheses around the left hand the apply. So if you cross off, if you just write the pure word in white, and you write the funny apply in white as a function application, then you'll see this is just cons applied to f of x applied to traverse of x. So it looks like the identity function. So what you do here is you just use the identity function in a slightly different color, and what you get is traversal. That's quite magical, I think. Very hard about what the traversal should be to get at least one traversal. There's one that sort of follows the structure of the data type in the obvious way. Lists are built with a particular bias, and this is going to be traversal with that bias. You can write a traversal with different biases. You have to work a bit harder to do that, but there's one very natural one that sort of falls out of the data type definition. Right. Yes, please do put it in the collar. You were right all along.
Okay, now we know.
Right. So here it is again in the less convenient notation, and you'll see why the convenient one is convenient here. So with apologies, I'm going to be showing you the less convenient notation, because what I'm showing you is not so much using it, but defining instances of it. But instead of pure and funny apply, we're going to have unit, which is the void returning thing, and this pairing that takes an f of a and an f of b and makes an f of a b's. And so then you need pairs and curries and uncurries and so on. But that's the price we pay for this slightly simpler interface we're going to be defining. Now here's trees. Here's a data type of trees. There are forests. They're mutually recursive. So a tree consists of a label and a forest of children, and a forest is just a list of trees. Trees are defined in terms of forests are defined in terms of trees. We will see a bunch of functions on trees, and they're all going to follow that pattern. The function on trees will be defined in terms of the corresponding function on forests, and the one on forest in terms of the corresponding function on tree. So here's a tree, root label 3, 2 children with labels, root labels 1 and 4, and a picture of that tree. And here's traversal for that tree. I can't remember if I've got the Haskell one on here as well. No, I haven't. So this is the traversal in the less convenient syntax, but you saw how it worked for lists, and presumably you can follow how this is going to work here. But there's a traversal for trees, which is what you're defining by making an instance of the type class, with a local definition of a traversal for forests. And traversal for trees depends on traversal for forests, and traversal for forests depends on traversal for trees. And so it's just going to traverse every element in one of these trees in the obvious way. You'll visit the root node first, and then you'll traverse each of the children in turn. So you'll traverse the entirety of the left child, and then the entirety of the next child, and the entirety of the third child, and so on. That will be a depth first traversal. And so it's very similar in principle to the list traversal. In fact, a forest is a list of trees. So to traverse a forest, you traverse every tree in that forest one after the other. So it's a traverse with a traverse. But the outermost traverse here is list traverse because it's a forest, and the innermost one is tree traverse because it's traversing a tree. They're written with the same word, but the Haskell type class resolution mechanism will pick the right instance of traverse for the type. That's the type-driven bit. And it's so formulaic that you don't even need to write this. you can derive traversable. There's an obvious definition that just arises from the algebraic data type definition. So you don't have to think about that at all. That's depth first. What about breadth first? That's a bit more tricky. And this is something I've sort of bashed my head off and on for, well, since my first ICFP. So for 25 years I've been bashing my head off this. And I'm not going to take you through all those painful head bashing exercises unless you ask me. But perhaps you can see, perhaps you would sit down and write it this way. You know how to do breadth first enumeration of things. It's a queue, basically. You make a queue, you put the tree in the queue, you take things off the queue, deal with one element and put all the other things back at the end of the queue. And so you don't get to them until you've dealt with the highest priority things for everything else that was already in the queue. So that does breadth first enumeration, but it doesn't follow the structure of the tree in any obvious way at all. How do you do something that doesn't just enumerate the elements of the tree, but gives you back a tree of the same shape again with some other stuff done to it? So it does a breadth first traversal of the tree. So the example I'm going to show you is breadth first relabeling. In fact, the example I'm not going to show you is breadth first relabeling, where you've got a stream of new elements, and you go over the tree and apply these, stick these new elements into the tree one by one in breadth first order, and get back a tree of the same shape as you started, but with new elements. So this isn't going to do that because you just get a list out of it. You've lost the tree structure by sticking things in queues. You can do it, if you try hard enough, by splitting the tree into its shape and contents. So the shape is just a tree of unit values, no payload. The contents is just a list of elements. So if you can enumerate to get the list of elements, then you can get the list of elements in, well, they'll come out in breadth first order. And then you can do whatever you like to that list of elements as a list. And particularly, you can do a left to right traverse over it. And because they came from the tree in breadth first order, that will be hitting them in breadth first tree order. So you could go and fiddle with each of the elements one by one, and then you can sort of undo the shape and contents thing to repopulate the tree from its contents. And you can do that, and shape and contents are both nicely structural things, and the undoing of shape and contents is also nicely structural, but it's multi-pass, and that's a bit awkward. Now, there's a very clever circular program to do it, which is due to Geraint Jones, and that was what I was working on for my that first ICFP paper, where you relabel the tree in breadth first order, but so suppose you magically had the list of things that you need to use on the first level, the list of things that you need to use on the second level, the list of things that you need to use on the third level, all carefully partitioned, split up from a long list. If you magically had that, then breadth first relabeling is not difficult, because it can be structural now. You've just got this list of lists of the magic ingredients you need, and you just kind of zip it across the tree, and it works out very nicely. The question is, where does the magic come from? And the magic comes from, you can construct that list of lists in the process of doing using the list of lists. And you can think of it, which is the story Geraint tells me of how he came up with it. It was Christmas, and there's a Christmas tree, and you've got a piece of tinsel, and you put it around the tree, and it goes around the back of the tree, and then what's left of the tinsel goes around the next level of the tree. And so what comes out of the other side, unused, of the stuff that you need, is what you need to feed back in the next level down. And you can write a nice, lazy, circular program to do that, and Geraint does, and it's a one-liner, and it's fantastic. But it's lazy and perverse, and it's hard to see what's going on. It's hard to see how you might come up with that if you weren't already decorating a Christmas tree. And it seems to be essentially about laziness. Now, here's another thing of a circular program. This is what's called the repmin problem, and it's one that was introduced by Richard Byrd in about 1984 as an argument for why you want lazy programming and let recs in your programming language. So the problem here is you've got a tree with integers, and you want to replace all the integers in the tree with the smallest integer that's in the tree. So here's a tree with integers, the same one we had before. We're going to replace everything by 1, which happens to be the smallest thing in the tree. Now, of course, it's straightforward to do that. You go over the tree once and you find the smallest thing, and then you go over the tree a second time with just a map and replace all the things with that one thing. But the challenge is to do it in a single pass rather than 2. And Richard, so we had this paper on, well, I can't remember the title of the paper now, something about circular programs in 1984, and he said, well, look, here's a clever way of doing it. Forget about that line for the moment. There's auxiliaries here that are doing all the work, and again, there's an auxiliary for trees and an auxiliary for forests, and the tree one depends on the forest one, and the forest one depends on the tree one. They're mutually recursive, but that's all productive because it's all things depending on the corresponding function on the smaller things. What this does is it takes a tree of ints and some arbitrary thing of type A and gives you back the minimum int and a new tree where all the elements are being replaced by that one thing of type A. Perfectly straightforward. And this is a perfectly straightforward program for doing it. There's no circular programming or anything here. It's what you'd get by splitting this in 2. So this is, given a tree of ints, you can work out the minimum. That's easy. Given a tree of ints and an A, you can make a tree of A's. That's easy. And they both follow the same recursion pattern over the trees, so you can tuple them together. That's called the banana split theorem in the squiggle tradition. So that's all easy. That's all straightforward. And the clever thing is, well, where does this A come from that you're going to replace everything in the tree with? It's the output from the minimum part. And so that's what happens up here. We're going to call this args function on our tree with some m. What's m? Well, it's the result of doing the recursive call. Well, not the recursive call. It's the result of doing the call. So this let needs to be a let rec. And it only works because the m that comes out is not dependent on the m, sorry, the other way around. The m that comes out is not dependent on the m that went in. If I put in undefined as the m that goes in, I'll still get a proper m coming out, and that's where the productivity of the cyclic program comes from. So Richard talked about this, I presume, at the working group 2.1 meetings that he was going to, that I wasn't because it was before my time. Another member of 2.1, Alberto Peterossi, said, well, that's very interesting, but much more complicated than it needs to be. Here's another way of doing it. And Alberto's program, written in Pascal, which didn't exist when Alberto wrote it, so I'm retrospective consistency kind of thing. The difference is this auxiliary function takes a tree of ints and gives you back a pair with the int, which is the minimum as before, and a function, the function that is the dependency on the thing to be replaced to the tree of replacements. And it's this dependency that Alberto said, that's all you need. You don't need let recs. You just need higher order stuff. It's just a functional program. And now it's just an ordinary eager functional program. And the difference up here is you run awks on a tree and you get a pair with a function u and a minimum m, and then you just apply u to m. So you uncurry apply on that pair. And that's not circular. You call awks on T, you get a pair um, neither of those is used in the call, so an ordinary let works. And those two stories, breadth first traversal of trees and this repmin thing, are related, and that's the point of my talk. So perhaps you can guess, perhaps you can write it in your head if you're familiar with the traverse. Each of these is, well, so let's say each component of this, one to compute the minimum and the next one to do the replacing, each of those is independently a traversal over the tree. So you can compute the minimum by just traversing the tree in any order, in fact, because min is commutative, and you get the minimum element. And you can also, independently of that, traverse the tree to replace something. That's just a map, so that's a traverse too. And what's going on here is those two traversals are being fused into one. So rather than two recursive calls, or two calls, one to do min and one to do replace, there's one call, and this is the sense in which Richard is solving his problem about doing it in one, with one traversal of the tree rather than two. Now, don't ask me to justify why that's any more efficient. It's not, in fact. The faster way of doing it is to do it with two traversals. So it's a kind of coding trick. And this is a very artificial problem, but it's an artificial problem that's an abstraction of a real problem in compiler writing, where you want to do a traversal over the AST to figure out all the declarations, and then using that information find out all the uses and link them up to their declarations, which might be forwards and backwards references. So it's about fusing together two traversals into one traversal. So how does that work? So if I've got a single structure, T, a tree, and two traversals that I'd like to do it on it, F and G are the traversal bodies, so F turns my A's into B's with some effects, and G turns my A's into C's with some more effects of the same kind. Can I do that with not two traversals but one traversal? Can I go over my tree and turn all the A's into B's and C's in one traversal, because I'm doing the same order of traversal for both of them? And that will give me a tree of BC pairs with effects from F. And then I want to unzip those two trees to get the tree of B's and the tree of C's that is what's supposed to happen over here. But because I compute both of them in the same order, can I do it with just one traversal rather than two? And the answer is obviously no, in general, because they'll give you different interleavings of effects. These are effectful traversals over trees. So this one, if the class of effects is IO, then this will do a whole bunch of B kinds of IO, so the kinds of IO from this part of the computation, and then all the other kinds of IO. So it'll do some IO in French, and then some other IO in German, and all the French stuff will precede all the German stuff. Whereas this one will do a bit of French and a bit of German and a bit of French and a bit of German. So obviously those are going to be different, so that's not going to work. If it were not IO, but something that were commutative, a commutative class of effects, then that wouldn't matter. So if you were doing probabilities or something like that, or just reading from some context, the interleaving is not observable, and those two, it looks more plausible that they might be the same, but that's very restrictive, and it doesn't allow us to do all the non-commutative effects, for example, tree relabeling and things like that. So here's an intermediate point. The interleaving is also irrelevant, so there's hope for this equation. If even when big F here, the class of effects, and I apologize for my naming conventions, the class of effects is non-commutative, like IO, but the things that F does and the things that G does in that class of effects do happen to commute with each other. And what that means is, if I do F on X and get a result, and G on Y, and then G on Y and get a result, that's the same as doing G on Y and getting the result, and then F on X and getting the result. My results were the wrong way around here, so I twist. That's the swap action on pairs. here you get f of x then g of x, here you get g of x then f of x, and what you want is for those to be the same. So that's the statement of the condition f of x commute with g of x. And there's a theorem, which is in our paper, that says if f of x commute with g of x, then these two traversals fuse. So when does that happen? Well, one place where it happens, and what the talk is about, is if the class of computations is a two-phase class of computations, so a class of two-phase computations, let me say. Do some things now, do some things later. And what f says is do things now, and what g says is do things later. Just to say, if I tell you to do x now and do y later, that's the same as telling you to do y later and do x now. My two instructions have commuted, and then the overall behavior when you follow out your list of your to-do list is going to be the same. So this two-phase computation is the trick to getting this traversal to work, this traversal fusion to work. How can we implement that? Well, it turns out that what you want is something that captures two computations, and TyDe convolution is the thing. What is TyDe convolution? Well, I have no intuition for where this comes from in category theory, but this is something that a certain person called TyDe wrote about, it has some connections with convolution that perhaps you can see if you stare at that hard enough. It's a funny Haskell data type. There's just one constructor. These f and the g are classes of effects. So like monads or applicative functors. So a program that has some effects in one class f and some other effects in another class g, different classes in general, and produces some results of type C, can be obtained in the following way. A program that does f things and returns a result of type A, another program that does G things and returns results of type B, and a post-processor that turns AB pairs into C. So this post-processing thing is sometimes called a co-Uneda trick. It's a way to turn this into a functor when it isn't obviously a functor. It now delivers things of type C, and if you know how to turn C's into D's, then there's an obvious way to make it return things of type D. You just post-compose the function, the wrapper. It doesn't matter what you do with the internal stuff. Now, it turns out that if f is an applicative functor and g is an applicative functor, then TyDe is an applicative functor. Actually, that's very deep. I told you the joke about monads being monoids in the category of endofunctors. There isn't just one category of endofunctors. There's categories of endofunctors with different monoidal categories of endofunctors with different monoidal structures. And if you use composition, then the monoids are monads. But if you use this, TyDe convolution as your binary operator, TyDe is a binary operator on applicative functors, then the monoids are the applicative functors. Applicative functors are also just monoids in the monoidal category of endofunctors, just a different monoidal category of endofunctors. So that's cute, not helpful perhaps, if you haven't seen it before. So that is Mara Yaskeliov again and Ezekiel Rivas, I think, made that observation. Very nice work again. So TyDe convolution is the thing. And so here, and TyDe convolutions, you can think of them as being two-phase computations. One of these TyDe convolution thingies has within it a computation with effects of class F, and some more computation with effects of class G. I'm going to think of those as the two phases. And so, in particular, if I've got only a computation with effects of class F, I can treat it as one of these two-phase things that just skips the second phase, the G phase. And conversely, if I've got something that only is G's, then I can make it one of these that just skips in the F phase. Now, unit here is the thing from applicative functors. It's the one that returns void and has no effects. That's the skip. And again, apologies perhaps for naming convention, unit L and unit R are just the pure things that explain how pairs are monoidal. So unit R is the right unit of pairing with the unit type. But the nifty thing about this is that the computations in different phases commute. It's just the do X now, do Y later. If I tell you to put X's in phase 1 and then Y's in phase 2, that's the same as telling you to put Y's in phase 2 and X's in phase 1, but the plain data results you'll get out will be in the wrong order. You just twist the data around. Moreover, if your two classes of effects, F and G, are in fact the same, you can run one of these day computations. You run the first phase, and then you run the second phase. And it's just an F computation followed by another F computation, so you just do sequential composition of those two classes of computation. So here's an example. I can say hello world in two phases. I can say, for phase 1 we're going to say hello, phase 2 we're going to say world. Now run those one after the other, and it'll say hello world. But I can also say, in phase 2 we're going to say world, and in phase 1 we're going to say hello. Now run them one after the other, we will again get hello world. And you can even mix them up. So you can say in phase 1 we're going to say hell, phase 2 we're going to say world, and phase 1 we're going to say hello, and run them one after the other, and you'll get hello world again. These phase 1 and phase 2 are orthogonal to the sequential compositions you do in each phase. So you can sequence a bunch of things together in phase 1. That's not commutative because it's sequencing. You can sequence a bunch of things together in phase 2. That's also not commutative. But the specification of the things you do in phase 1 with the things you do in phase 2 can interleave arbitrarily. So here's how you use that to solve the repmin problem. We're going to, from our tree, we're going to construct a two-phase computation. And I'm not going to show you all the steps about this unless you ask me about it, but let me give you the high-level view. It's a two-phase computation. There are two phases. In the first phase, we're going to go over the tree and collect the minimum value. So in Haskell, the idiomatic way of doing that is using the writer monad. It's a monad, but that means it's also an applicative functor. That's fine. And we're going to write ints, and we're going to use min as the monoidal operation in doing so. So there's a wrapper, a new type wrapper called min that does that for you. So this is a computation that in phase 1 is going to go over and collect the minimum value in the tree. In phase 2, we're going to read from a context, and that will be just picking the value that you computed as it happens in the minimum phase, and that's going to replace every element in the tree with the constant thing from the context. So write as a monad, read as a monad, min gives you a monoid. It tells you which monoidal operation on a carrier type for which there are many monoids you might have chosen. There's a two-phase thing. One phase gathers a whole bunch of information, and then the second phase scatters that information across the data structure. Each phase is an instance of traversal. So you can obviously traverse the tree and collect the minimum by visiting every element once. And you can also obviously traverse the tree and replace every element by a constant by visiting every element exactly once. Moreover, the gathering is going to be phase 1, the scattering is going to be phase 2, so the bodies are in different phases, so they commute, so the two traversals fuse to give you one traversal. So repmin orcs is a single traverse, computing something in this fancy day type. Then, given something in this fancy day type, it doesn't matter now whether it's about mins and monoids and so on, just some type S. You've got something that writes, in phase 1 writes an S, and then some phase 2 later reads from that S. you can unpack the day thing. So now X's is a writer computation, Y's is a reader computation, and H is the wrapper, the co-Yonader wrapper for them. Let's undo the representation of writers, and that gives us a value and the written output. Let's undo the representation of readers, and that gives you a function from some context. So let's use S as the thing we pass in as the value of that context, and then we'll get out of that a Y. So we get an XY pair, and the wrapper is exactly the right thing to apply to that to produce a result. But that let has to be a let rec again, because where's this S come from? As input on the right-hand side, it's the output on the left-hand side. But if you do this extraction on that retmin function, then what you get is sort of quite obviously Richard's retmin program. This is the cyclic bit. And this is all the perfectly straightforward, not cyclic, ordinary equational reasoning, squiggly stuff, all very well established. It's only this that is the tricky thing in Richard's paper. And the difference between Richard's paper and Alberto's presentation of it, Alberto's paper, is not to extract these two things in parallel, but to extract them sequentially, one after the other. You extract the first thing, you get a pair XS, you extract the second thing using S, and get a Y, and then post-process X and Y with H. And I don't have them both on the same slides, so you can't see, but well, you can see that this is no longer cyclic. You don't need a let rec anymore. The dependency on this S here on that definition up there is just an ordinary dependency. So a non-recursive let suffices. And Alberto's program is just doing this extraction on the same retmin orcs. But also, perhaps, so it would be helpful to have them both on the same slide. In Haskell, this is the same as that. The dependencies it produces between variables, between declarations and uses, is exactly the same whether you do this two lets in parallel or the one let after another. Only true in Haskell, because this Haskell's let is a let rec. But this is the tweak you need to turn Richard's fancy, clever Haskell only, lazy only program into something that works in an eager language. So that's two-phase computations. You can generalize it to multiple phases. So this is a data type where there's a statically unbounded number of phases. Now it has to be homogeneous. They all have to be in the same class of effects F, because I don't know how to pass in something that will post-process an unboundedly large collection of different classes of effect. But there's something that has only a value, no effectful phases, and there's something that says if I've got an effectful phase and some more effectful phases, then I can make a one longer collection of effectful phases. So think of this as a chain, and this is the end of the chain, and each link of the chain is one more effectful computation, one more phase, and one of these co-Yonader post-processors that puts the results together. So for example, if I have a plain value Z of type A and an effectful computation Y that returns B's with effects in F, and a post-processor K that puts B's and A's together to make C's, then this bit is an effectful computation that returns C's. And then if I have another computation that returns D's and another post-processor that puts D's and C's together to make E's, then the whole thing is a computation that returns E's. And this line here is obviously doing a day convolution kind of thing. So what's happening here is, in fact, this is an iterated day convolution, a homogeneous iterated deconvolution. So very like lists, which are just homogeneous iterated pairing of things. There's an empty list, and you can pair together a head and a tail to make a longer list. Cons together a head and a tail to get a longer list. Now, this data type, phases, is not new. And in fact, it's the data type that underlies the free applicative functor on a given base functor. So if you've got some arbitrary functor f, not classes of effects necessarily, you can make an applicative using this data type. So this data type is one of the ones that appears in a paper by Capriotti and Capozzi about free applicative functors that was in Mathematically Structured Functional Programming some years ago. And this is, so there are various different representations. This is kind of cons free applicatives where the recursive thing is in the right-hand side of the pair, but you could have one where the recursive thing is in the left-hand side of the pair and have SNOC kind of free applicatives as well. And I think there are other ways of doing it too. This is one of the ones in Capriotti and Capozzi's paper, and this is the applicative instance. Now, there's a lot of plumbing going on here, and I'm not going to talk through it. But this plumbing is why I've got this awkward presentation, because the plumbing is even worse in the higher order presentation, the one where these things are functions. At least here it's just pairs that we're dealing with. But what the free applicative does is concatenate. So perhaps you can see here, this is like list append. When you get to the end of the first list, you sort of have all the structure of the second list. And if you're not at the end of the first list, then you strip one thing off x's and you sort of recursively append y's and z's together. So this is assembling computations by chaining them together, sequential composition. And that's what the free applicative does. But that's not what we want here, because I want to say to the left side of my tree, in phase 1 do this, in phase 2 do that, in phase 3 do something else. The right side of the tree, I want to say in phase 1 do this, in phase 2 do that, in phase 3 do something else. I don't want to end up with 6 phases. I want to end up with 3 phases. So what I want to do is not concatenation, but zipping. And it's in fact what I call a long zip, and what I called a long zip in my ICFP 1998 paper. So nobody else but me likes this, but I think this should be standard stuff. Ordinary Haskell zip takes 2 lists which might be of different lengths, and when one runs out, the result runs out. You get an output that's the shorter, as long as the shorter of the 2 arguments. Long zip gives you an output that is, whose length is the longer of your 2 arguments. What do you do when one runs out? Well, you just copy things from one list, from the other list, input list, to the output. That means long zip has to be homogeneous rather than heterogeneous. It takes a list of length A's of one length, another list of A's of another length, and glues them together into a long list of A's. And where you've got A's in both cases, you need a binary operator to put them together. And where one runs out, you just copy the other one across. And that's what's going on here. So we have some collection of computation in phases, some other collection of computations in phases. They're these chain things, and you put together the first things in each phase, and the first things in each side, and then the second phase things in each side, and the third phase things in each side, sequentially composing 2 things in the same phase. And then when one runs out and the other's still going, well, you just copy that across to the result. And that's what this does, trust me, and don't try and read it. So now, phases is arbitrarily many phases, so you can do the kinds of things you could do with just 2 phases, except there's more of them. So a 2-phase thing, a homogeneous 2-phase thing, is a multi-phase thing. It's just a multi-phase thing with 2 links in it. So it's a list of length 2. Pairs are lists of length 2. homogeneous pairs, are lists of length 2. And if you've got an int and a effectful computation, you can say do this at phase I. So all you need to know now how to do that, it's inductive on the I. You need to be able to say how to do something at phase 1, that's now, and how to do something later, which postpones it one level down. And then, well, so here's an example of something you can do with more than 2 phases. I had to think a bit about this, but actually this is another one of the examples that's in Richard's paper from 1984 and picked up by Alberto in 1985-6. As Richard said, here's another rep mini kind of thing. Here's something for which letrec would be nice, and Alberto said, no, you don't need letrec. It can do it just as well this way. So this is a 3-phase computation. The problem is you've got a tree of elements of some ordered type. You want to extract the elements to a list, sort the list, and put the elements back on the tree to get a tree of the same shape, but now with sorted from left to right. And of course, you can do just that. You can go over the tree in one pass with a traversal to collect all the elements. In phase 2, you don't touch the tree, you just do something on this collection of elements. And in phase 3, you go over the list again, go over the tree again, taking things out of a list one by one. Now, I'm doing this. So for phases, it needs to be homogeneous now rather than heterogeneous. So I need to figure out how to do that in a homogeneous class of effects. I'm going to use state. There'll be a list of where I'm storing things and sorting things. And I'm going to push things onto this list and then pop them off the list. You do the same trick. There's a phase 1, a phase 2, a phase 3. They all commute with each other because they're in different phases. So let's put the sorting first, and then the traverse with push and the traverse with pop. And the traverse with push is a whole traverse in phase 1, but that's the same as just an ordinary traverse where the effects are stated to be in phase 1. That is to say, phase 1 of a traverse of something is the same as traverse of phase 1 of that something. Phase 1 and traverse commute, and nothing special about 1. Phase I and traverse commute. I can say all in one go, do this traversal at stage 3, or I can say now look at the tree and stick a whole bunch of things in at phase 3. So then we have a modify. In fact, we do have the calculation. No, I don't have the calculation. Ask me later about the calculation. You have a phase 1 with the traverse, a phase 3 with the traverse, so you can make a traverse with a phase 1 and a traverse with a phase 3, and because the bodies are phase 1 and phase 3, they commute, and so those 2 traversals fuse to make one traversal, and you get this. In phase 2, we're going to modify the stored state, which is a list. I'm going to sort it, and otherwise, we're going to traverse the tree and we're going to push each element in phase 1 and pop a different element in phase 3. And that is manifestly a single traversal over the tree. There's only one traverse in there, which will sort the elements of the tree. So that's just the orgs thing, but you just have to run the phases one after the other. They're all in the state monad so that you can just flatten them all. Now back to breadth first traversal. The same kind of thing applies, except slightly different here. This is 3 phases and always 3 phases. It doesn't matter how big your tree is. Phase 1, we collect things. Phase 2, we don't look at the tree, we sort things. Phase 3, we put them back. Here, I'm going to have a statically unbounded number of phases. There's going to be 1 phase for each level of the tree. So this BFT orcs is the thing that makes the phases, but they're all with the same class of effects, and so I'm just going to flatten them, do them one after the other in the end. And here's what it does. It's just traversal, except these root elements you do now, and all the children you do later. And that looks very like the depth first one. In fact, let me show you. I've got the same thing in the Haskell presentation, so let me abandon my my categorical presentation of effectful things now, back to Connor's notation. This is the ordinary depth-first traversal of trees that we saw at the beginning of the talk. Visit the root, visit each of the children. Here I'm calling it DFT, but it's the instance of traverse we had for trees. And you put them together with node. So there's a pure and funny applies. And if you just stick now here and later there, then you get breadth-first traversal. And I think that's quite remarkable. I'm delighted at how quickly and easily, I mean, how simple that program is, how tidy that program is. And then the fancy breadth-first relabeling is you just need breadth-first traversal. Once you can do breadth-first traversal, then breadth-first relabeling is easy. You feed in, let's say, a stream and an infinite list of new labels, just so we don't have to worry about it running out. And at each element, you just pop something off the stream. And the breadth-first labeling calls breadth-first traversal, and it's the breadth-first traversal that deals with the breadth-firstiness. That's what it's supposed to do. So all you have to deal with is the pop here. So Geraint's beautiful circular lazy functional program is redundant now because we've got this phasors thing. I should say I was delighted to come up with this, with my co-authors, to come up with this fancy breadth-first program, which is really tidy and really nice and elegant. Then I discovered that wasn't the first person to do that. So there's a guy called Craig Easterly, who's written I don't know who he is, written a Haskell library of tree traversals, and this is in there. So it's prior work, nothing new under the sun. But it doesn't, I mean, I can't claim to be the originator of it, but it's still just as pretty as it was when Craig came up with it rather than me. And I'm going to stop there. I've had my hour. Deconvolution is something worth knowing about, even though it's a bit head-scratchy. But it's the natural monoidal structure that sits underneath applicative functors. And it is what you need for multi-phase computation. So two-phase computations are just deconvolution. And multi-phase computation is just iterating that binary operator. It's a funny applicative instance. Maybe I didn't emphasize this enough. The free applicative has the premise that all you need is f is a functor, and then you can make something that's an applicative functor, and you get the free construction, just like free monads give you a monad structure on something that was not monadic to start with. Let me go back. That's the free applicative, Kaposi and Capriotti. This one, R1, the one that zips, requires you to be able to pair together things at the same level. And so that requires f itself already to be applicative. So if it's applicative horizontally, if you like, here's how to make it applicative vertically. So the types are different, as well as the definitions being different. Richard had this thing about lazy circular functional programs, and Alberto, much less well known in our community because he's really a logic programming guy, said here's how to do it just with higher order features. I didn't know that when I started this work a year or two ago, despite being a member of 2.1 and knowing Alberto very well. It just completely missed me. I think Alberto's papers are very worth reading. Olivier Domvie has written a little bit about this and comparing these two, so I should have known it if only through Olivier Domvie's work. But I really like the fact that the difference between Richard's and Alberto's RepMin programs is just a matter of staging and how you flatten that staging at the end. And I really also like this breadth-first traversal, Craig Easterly's invention. Now, I have some other thoughts which are sort of still mulling around in my head about software architecture and choreography. These multi-phase computations are a collection of phases indexed by natural number, the level. but there's nothing really that requires it to be numbers, and we're not doing any arithmetic on the numbers. So I have a conjecture about richer structures of indexing. So choreography is a kind of multi-site, multi-location computation, and this is just some computations indexed by their location. So if you want to see if I can make some sense of that, come along to a new workshop on functional software architecture on Friday, where I'm also giving a talk about this. It's a shorter talk, and I'll skip over the TyDe-ish details and try and say something interesting about choreography and things. So my colleagues, the paper, it's on my webpage, and this the traversal stuff is stuff I did with Richard. The Repmin stuff is stuff that I inherited from Richard. It was before my time, but influential on me. This paper is dedicated to Richard's memory. Thank you.
Thank you, Jeremy. Any question? You can, if you're online, you can ask them on Discord, and I will replay them back.
Alan Jeffrey, I'm from Roblox. That was very nice. There was a lot of text on those slides. I'm wondering, can I get some pretty pictures of this? Is there a connection over to string diagrams?
That's an excellent question. I have no idea. There's a lot of categorical structure in here, so you would absolutely hope so. But I don't know, you're the expert. Is there a string diagram story?
I could make a guess.
Yes.
Just wondering if you'd already
No, I haven't already
done the grunt work.
No. Brent.
Hey Jeremy, thanks. That was a lot of fun. Have you thought about? I wonder if you could get multi-phase computations with heterogeneous effects by sort of indexing by a type-level list of applicative functors. Do you think that would work?
So you can certainly do that, and in fact, it's something I've written about. So I was written about in the abstract for FunArch because one of the reviewers asked about it there. So you can, but then you need some indexed way of running it. So how do you, if I've got an F effect and a G effect and an H effect and a K effect and so on, how do I extract them and do them one after the other? Well, you could construct that too. But the nice thing about applicative functors is that they compose in exactly the way that monads don't. So if I've got an F effect here and a G effect there, then I can make one combined class of effects in which both of these appear. In fact, it's just the TyDe convolution. So what I'm doing, if you like, is already embedding in the homogenizer that would take your heterogeneous ideas and inject them all into some homogeneous supertype.
Hi, Will Creighton from Brown.
Hi.
And thank you for the great talk. Can you go to the slide where you showed the type signature of the TyDe convolution implementation of Repmin? Yes. Is this type signature constrained enough that if you assume that writer, min, and reader are implemented as you expect, the only valid implementation of this type is sort of performs repmin? Because, like, this wasn't true, I think, of the later type signatures where you use the phases type class.
It's not true here either, because of this being fixed int. Nothing stops me, the reader, taking the int and squaring it, or using a different int.
Right.
But here, the S type is now polymorphic, so you can't depend on anything about the S type.
Right.
So maybe if I gave it this polymorphic type, then the implementation I've got is the only implementation.
Right. I just thought it was interesting how much of the computational structure becomes reflected in the type
Yes,
signature,
yes.
and then how much it constrains it. Right?
Yes, that's a very TyDe question.
Mm-hmm.
Haven't thought about it, but certainly you would need the polymorphic one.
Right.
But I don't know if that's enough.
Oh, it's an interesting connection. Thank you.
Yeah, hi, I'm Peter Diemann from Freiburg. I also had the question about the heterogeneous phases, but that was already gone. But I was wondering, so as far as I remember, Olivier d'Anville had the problem to show that the two traversals are equal. I mean, that the circular program is equivalent to the one where things are sequentialized. So as far as I understand what you're saying, so this is solved by this approach, isn't it?
Yes, yes. I think this is much nicer than Olivier's stuff because there's the sort of categorical structure, the algebraic structure, that is not Olivier's bag. So he's just done it with flattened equational reasoning with functional programs. So he has shown that, I guess, that they're the same, but the argument for that is much more low level than this one.
Yeah, excellent. Thank you.
Hi, hi, Neil Krishnaswamy from Cambridge. So, if you asked me, so I really enjoyed this talk. So, if you asked me, how do you do breadth first traversal?
Yep.
My answer would be, you put it in, you get the adjacency graph of the tree, and then you do some matrix multiplications.
Okay. That wouldn't have been my first guess.
And I was just wondering if you knew, is there like some connection between like sort of this kind of this style of graph algorithms through
linear algebra.
Yeah.
I don't know. I mean, there's a book on graph algorithms via linear algebra or something like that, which looks very interesting and is on my reading list. But it's input, not output, so far. Yeah, I don't know. And it would be nice to use this, in fact, for graph algorithms, because just before Richard died, he and I were working on this book on algorithm design with Haskell. There's whole chapters on breadth first and depth first traversals of graphs, which are all done using queues and stacks, as you might expect, the traditional way. There's a job to be done, a paper to be written perhaps, about maybe you could do it this other way. Richard would not have wanted that, and the book is resolutely simple, which is one of Richard's strengths, but so there's no monads in the book, there's no type classes in the book apart from ord and things like that, no new type classes. It's all how little do we need to get away with telling the functional programming story. So it's absolutely not an exploration of fancy Haskell features. But if you wanted to do an exploration of fancy Haskell features for algorithms, particularly graph algorithms, then yeah, nice idea, thank you.
Any other questions? Oh, yeah. You saw what I did here. I did a breadth first.
Yes.
Yeah, thanks. Yeah, Jennifer Pagan.
Hi, Jen.
So the goal that you were getting to was a single traversal of the tree, the list, the traversal. But it struck me when you were like in the example when you were calling run reader and run writer, and however for multi-phase computations, are those doing those computations, are you sort of effectively doing a structural traversal again in that later stage, or am I think I'm missing something, but I don't.
No, I think you're exactly seeing why people are always suspicious of Repmin as a convincing example. It's not very convincing. So Richard's cyclic program, I think it's harder to see what's going on. Alberto's higher order program makes it very clear. In one pass, you compute the minimum and a function that, given a new value, will give you back a tree. So that function embeds within it a whole tree structure, and if you give it a value, somehow it's going to have to make a whole tree out of it. So you haven't saved anything, you just moved that bump under the carpet into a different place. So I'm not offering this as an efficiency proving transformation or anything like that, and I don't think even Richard did that in 1984. It said, his argument was, this is a natural way of expressing the problem, and so we should have letrec in our language to allow us to do this. Now, you could argue with that claim even. But I do think, so that's my software architecture story. Sometimes the neatest way of expressing the computation you want to do is completely orthogonal to the way you want to end up actually executing it. So I'd like to be able to say here, there's some stuff for phase 1 and some stuff for phase 3, and there's some stuff for phase 2 and phase 4. And you see this in literate programming as well, where, I mean, Ruth's idea for writing programs, Tech and Co were written in Pascal to start with, and Pascal had very strict constraints on the order of the definitions in your program. You had to have all the constants and then all the types and then all the declarations. But in explaining a program, you wanted to say, well, here's a constant and a type and a declaration for this data structure, and here's some more constants, types, and declarations for other data structures. So you'd like to be able to specify that in the sort of natural logical reader order, and something else rearranges them for the Pascal compiler. And similarly, that's what choreographic languages do. You write one unified program for the whole choreography, which then gets endpoint projection is the thing that factors it off into, well, you go and do this bit and you go and do that bit. And if you all talk to each other as we've discussed, then the book will be sold, or whatever it is that your choreography was for. So it's not an efficiency thing, it's an expressivity thing. What's the right way of describing your computation, your problem? But great question, thank you.
Any other question? Oh. You're just making me run.
Gabriel Ardan from Indria. Thank you, it was very interesting. I like the connection with tierless programming, but that's just my thing. I was wondering, so one thing you do when you go from Richard's program to the next one is basically you're forced to use higher order.
Yes.
Which is, as you said, pretty bad for efficiency.
Yes.
I was wondering if there is a way to recover that without going to laziness. And my instinct would be algebraic effects, but I wonder if we can do that, because it seems a bit tricky.
Well, that's another interesting question, because there's another little bit of my brain that's going algebraic effects, and yeah, well, I don't know. We should have a chat. I've never thought of it, and I mean that's why I come to ICFP. I give a talk about X, and somebody sticks their hand up and says, "Didn't you write about Y?" And aren't X and Y related? And I go, "Are they? Oh, that's nice." So thank you. Don't know.
Any remaining question? No? So I didn't see any question on Discord, but there's a comment for you, a gentle comment. So I invite you to hello there. So I think that's it for our first session. Thanks again, Jeremy.
Thank you.
So there will be coffee. I think it's at 10:30, and it's in the ballroom, I think, downstairs. And I really need that coffee.
So if you imagine that our language is the ground before inviting later?
Okay, we'll be maybe start the session on type-driven types. So, one goal of the session, I guess, is to answer the question what it means type-driven types. And the first talk is we'll answer another question: is that what happen when you put linear types into the calculus of constructions, of inductive constructions?
Yeah.
That's kind of my take on this talk. So it will be given by Cheng Fu,
Yes.
and it's authored by Hongwei Shi.
Yeah.
So please go ahead.
Okay. Yeah. So hello everyone. My name is Shencheng Fu, and thanks for coming to my talk on the calculus of inductive linear constructions. This is a joint work between me and my advisor, Professor Hongwei Shi, and it builds on a lot of the lessons learned from the ATS programming language. If you have seen our paper, there's a lot of very gory technical details in there. So this talk aims to be the complete opposite of that and give a sort of high-level overview of the design choices that we made. So as the name of our work might suggest, we are heavily inspired by the calculus of constructions. And the calculus of constructions is a dependent type theory designed by Coquand and Huet. Types can abstract over terms, allowing for precise specification of its inhabitants. Here we have two of the most famous examples of that. We have the pi type, basically saying for all x of type A, there is something of type B. The sigma type says that there exists some x of type A, such that there is something of type B. Pauline and Coquand extend the calculus of constructions with schemes for inductively defined types, forming the calculus of inductive constructions, which I will refer to as CIC. So despite the great successes, no, I already got into too far into the talk. Okay, so the theory of CIC lies at the heart of popular proof assistants, such as Coq and Lean. Coq and Lean have seen great success in the formalization and verification of software systems in mathematics. Some of the most famous projects off the top of my head are ComCert, formalized C compiler written in Coq, the Rust Belt formalization of Rust inside of Coq. This is where all of the Iris framework actually originated from. And we have the four-color theorem proof in Coq, and this is where the MathComp library of mathematics inside of Coq originated from, is to prove the four-color theorem. And we have MathLib, which is a huge library of mechanized mathematics inside of Lean. However, despite the great success of applying Coq to software verification, we do believe that there is a bit of a disconnect between the CIC theorem and the software system it tries to verify. So CIC is inherently persistent, whereas programs verified are often stateful. So one can work around this by first encoding the syntax and semantics of the stateful programs they wish to verify into Coq, and then we can apply program logics such as Iris to reason about the state transformations. But on top of the really difficulty in coding work, which something like Iris is a very big engineering effort on itself, we also have to trust that the original program that we're verifying actually follows these idealized semantics, right? So what we wish to do is we wish to support stateful low-level programming directly in the dependently typed language without extra encoding work. So to accomplish this, we incorporate ideas from Girard's linear logic. And sort of the main tenets behind linear logic is that it restricts the structural rules of classical logic. So one of them says that objects cannot be discarded via the weakening rule, and then objects cannot be discarded via the contraction rule. So essentially, without these, when these two rules have been restricted, what happens is that you have a symmetry between introduction rules and elimination rules. But however, we'll see very shortly that merely restricting weakening and contraction is not enough to obtain a language with the memory guarantees that we design. So In many type systems inspired by linear logic, one finds these kinds of lollipop arrows with the following interpretation as a function type. So when we say A lolly B, this is the type of a function whose parameter of type A is used exactly once in the body of the function. So here's a very simple example of what we mean by this. So here we have a very simple lambda expression with a parameter x of type A and a body m of type B. And this says that the parameter x can only be used once inside of M. Okay. So what can we do with this? So it would seem that if we apply this linear lambda expression to some value v, that the v passed into x seems like it could be modified in place because it is used exactly once in M. But unfortunately, the parameter x being used exactly once inside of M itself does not actually exclude v from being referenced or used in the entire program. It just says it's being used locally once in M. It doesn't say anything about v being used in the entire program. So if we were to call a mutating function like free inside of M itself, then this could lead to the value v getting reclaimed prematurely, and you can run into different kinds of bugs. Additionally, function closures like the lambda expression themselves are resources at runtime. So how many times can we apply the linear lambda expression itself? So these are the questions that we would like to address. And in our type system, the modality, or linear or nonlinear, is an intrinsic property of the values themselves. And the variables that are in the language simply propagate the modality information originating from a value instead of actually determining it. And this ensures that the single pointer property holds for linear values globally, and it allows for safe in-place updates. So to determine the modality of a value, use a two-sorted universe hierarchy system, similarly to Krishnaswamy's, to classify all types as either linear or nonlinear. So we have the sort U of all nonlinear types and a sort L containing all linear types. Though I want to point out, in our system, we do not need adjoint connectives or modal operators to go between linear and nonlinear things. And basically just using these two sorts and the universe hierarchy system, we are able to do that. So more formally, the modality of types and their inhabiting terms are determined by a couple of typing judgments. So for types, we have here, we say A is a nonlinear type because it inhabits precisely the U sorted universe. And we say that B is a linear type because it inhabits the L sorted universe. And for the terms that inhabits A and B, so for M, which inhabits A, we say A is a nonlinear term. And for N that inhabits B, we say N is a linear term. So here you can also see that there's some annotations on the colons, and these simply help to propagate the information of the sorts from the universe level all the way down into the term level. So we can see at a glance that M is a nonlinear term because we can see that the annotation on the colon is a U, and N is a linear term because the annotation on the colon is an L. Okay, so now we have the universes sorted out. We can start talking about the functions that inhabit them. So a pi type in CILC is of the following form: pi x colon a dot b. And then between these we have some annotations, sort annotations, S, R, and T, that ranges over the sorts U and L. So for the first two, sorts S and R, they inform us of the modality on the domain and the codomain. And the sort T, on the other hand, it's an annotation on the pi type itself. So functions inhabiting the pi u universe, pi u type, are allowed to be used freely, and functions inhabiting the pi l type must be used exactly once. So these couple of annotations determine completely sort of the questions we have from before. So now we have the functional core of a linear dependent type systems whose values have intrinsically determined modality. So to encode data types in a general and canonical way, we include typing schemes inspired by CIC for defining inductive types. And both connectives from linear logic and intuitionistic dependent type theory can be uniformly encoded using these schemes. So here we define the tensor of linear logic and the linear sum. And also we have the intuitionistic sigma type. So by simply varying the sorts on the arities of the data type, we can define linear types and nonlinear types. The actual typing schemes presented in the paper is quite complicated, but as you can see with some type inference and stuff, the interface that we expose to the user of the language is actually pretty simple. And it's about as complicated as Cox. So now that we have a system for declaring inductive types, I want to turn our attention to their elimination principles. So in intuitionistic dependent type theories, one would use induction principles to perform primitive recursion over inductive types, right? So here we have the induction principle for natural numbers. Roughly speaking, this says for some proposition on natural numbers, if we have a proof H1 that the proposition holds on 0, and a proof H2 that says if the proposition holds on X, then it holds for Sx, then we can apply the induction principle and say that the proposition holds for all of the natural numbers, right? So I want to draw attention to this H2, the proof in the successor case or the inductive case. So notice here that the variable X here coming from the predecessor and the px, which is encoding the sort of the recursive induction step. Suppose our natural number was a linear type, and this is something that you can actually define in our language, though I don't know why you would do that. But such a principle would be unsound, because the x here, which refers to the predecessor, and this px here, the x is simultaneously being kept as x, and is also being used by the recursion or induction to compute the px. So if the nats were linear, then this will obviously violate the no contraction principle. So instead of using induction principles for data, we opted to use a guarded fixed point and case analysis for primitive recursion. So here we have a user-written recursor for the natural numbers. So fixed point on the recursor, taking in a natural number, perform case analysis. When it's 0, return the proof H1. If it's successor X, we offer the writer of the recursor a choice between X or Rx. So for linear data, a user must decide to either keep X or to use it to compute the Rx part. And for nonlinear data, we can simply just apply contraction and obtain both X and the recursor applied to Rx. So this means that fixed plus case is equivalent to induction principles for nonlinear data. And for existing theorem provers that support guarded fixed points, such as Koch and Agda, we do know that the bugs in the implementation of the guard checker has led to consistency issues in the past. However, we believe that this combination of fixed plus case is cleaner than the alternative solution of providing specialized elimination principles for all usage scenarios. So in conclusion, CILC is a type theory combining linear types and dependent types. Our type system includes typing schemes inspired by CIC to enable the encoding of both linear and nonlinear dependent inductive types. We have proven the usual standard theorems, confluence, subject reduction, strong normalization. And using a heap semantics in style of Turner and Wadler, we show that CILC safely manipulates the memory of linear values. The majority of our meta-theorems have been formalized in Coq, and we have implemented a prototype compiler inside of OCaml. And there is still ongoing work. So currently, CILC only supports dependency on nonlinear terms. Recent work such as QTT show the possibility of such an extension. However, there is a bit of a trade-off to such dependencies in that non-monadic I/O effects are no longer possible. Also, linearity allows for the addition of session type-based concurrency. The inclusion of dependent types in general can greatly increase the expressiveness of session protocols within a unified framework. And we plan to extend CILC with more features and improve its expressiveness. And again, thanks to everyone here for attending to my talk. I'll be more than happy to accept questions and suggestions regarding our work. Thank you.
We have some time for quite a few questions.
Thank you. So you pointed out in the last slide that it only supports dependency on nonlinear terms.
Yes.
Maybe you talked about that. Maybe you had that in an earlier slide as well. But what does that mean exactly?
Oh, so like if we write a pi type, right? Like a for all something, that for all the variable, if it's dependent, then that type has to be a nonlinear type. Like let's say, for instance, let me go back to the slide here. Yeah. So for this thing, if we were to write this pi type, then this A here has to be nonlinear if we were to use X inside of B. If A were linear, then X cannot be used inside of B. So X cannot be a bound variable inside of B.
Thank you.
Another question?
Hi, that was a nice talk. I was just curious if you have anything equivalent to the bang and linear logic in your system?
No.
Okay.
No. Because we just completely use the U-sort for nonlinear things. And we actually think that this is more close to what happens in reality. Because if we have two universes that are completely distinct, what happens is if we have a term that is in the U, we can apply like reference counting and garbage collection to those terms. And if it's in L, then we don't do that. We can just use manual memory management so we can get very efficient representations for the values inside of the L universe.
Have some notion of polymorphism over universes so
Oh,
that I can...
That's a very good question. That's a very good question. Actually, in the most recent versions of this, yes, we do. But it's not at the theoretical level. It's kind of like more like typing schemes where you can quantify over different sorts at top level functions. So when you apply them, it automatically infers the correct sorts, and then it applies the correctly instanced one. So basically, you do not have to write, but you can write a lot of these things that are generic over sorts. Yes.
So you're using sorts or kinds to distinguish between linear and nonlinear, but
Yep.
something like QTT uses things like modalities. Is there like a type operator? Do you have any sense of what the trade-offs are
Yes, 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 actually, yes. So in the past, I've did some implementation experiments with QTT. So the issue is in the way that we handle sort of the again, it's the pi types here. So in QTT, oh sorry, not the pi types, the lambda applications here. So in QTT, it marks x as 1, right? So you can use 1 only once inside of M. But if you pass a value into here, this value could be some nebulous thing that's defined elsewhere in the program. So even if you say, oh, this v is used twice, sorry, no, what's the QTT? The w many times, or a unlimited many times, and then you are allowed to apply v to here, but you can't do any optimizations inside of M to get rid of this x, right? Because if you do that, then your v becomes freed, and then you can't use, you're basically reclaim that v prematurely. So you can either do like a deep copy of of v whenever you apply it, so that this v, when you apply it, it's a new instance of v. But this is very costly in practice because deep copies are very costly.
I think the modal systems allow you to like create a box.
Yeah. But
to restrict v as long as, so not every v, I agree.
yeah.
You know,
But it's like, what do you take out of the box?
But if you make sure v stays in the box throughout the program, which is I
Yeah.
show you, that would give you more control.
Yeah. So what the box is essentially doing, it's storing data in there to recompute v every single time, right? So every time you fetch a v from the box, it's actually very expensive. So yeah, basically, yeah. But in reality, I think variables are actually the cheap things, because in implementation, we usually just pass around different pointers inside of the variables. So it doesn't really make sense to restrict how many times a variable can be used. The variables are linked to the values which we want to keep track of.
Okay, we can thank the speaker again and move to the next talk. So the next talk will be given by Mark. Of co-authors, so Fu, Blair, Zhang and Shi, and I think yes. Mark has a solution to simplify life with dependent types by introducing dynamic equality. Please go ahead.
Try. Hello? Okay, cool. My name's still Mark LeMay. You may recognize some of these people from the last presentation, so this may be a little bit worse. We'll see. Why would you want to do this? Well, dependent types are great. You can specify really important invariants you as the programmer want, and you can like keep index out of bounds from happening. Here's a little program in Agda. Hopefully you can kind of read it. And it repeats a number. It repeats, it makes a length index list of trues if you give it a number of that length. If you give it a number and give it a list of one more than that length, it'll give you the first thing of that list. And we know because of the type that it can't look at an empty list and get ahead. And you can build it all into one little program, and this is great. Unless you typed it in slightly wrong, in which case it doesn't work at all. So, when you hit a problem like this in Agda or some other system, usually you get an error. You can't get any type information out of the system. You can't use the REPL. You can't continue using the file and add things to the program you've already written. And this is because in these systems, generally speaking, the 1 plus x and x plus 1 are not definitionally equal. So how should you handle definitional equalities during runtime, type checking? A lot of people have a lot of good answers to this question, but I think we're asking sort of the wrong question. So why would we want to do this at type checking at all? Type checking generally needs to be extremely fast for programmers to be happy with it. Our equalities are almost always going to be undecidable. It's just a recipe for misery, basically. So for this talk, we're going to suggest, instead of trying to deal with this at compile time or type checking time, why not warn with the same information you would get at the traditionally, and just put checks in when you need it so that if it pumps into something at runtime, you get a runtime error, possibly with the exact witness of inequality that shows you were wrong and a pointer to the warning that you should have listened to in the first place. So if I can get you to buy in, at least for the rest of this talk, that this is something worth doing, let me explain roughly how we did it. So we have sort of a standard architecture where we have a surface language, an elaboration procedure, and a cast language. And just so we're all syntactically on the same page, let's look at what the surface language consists of. It was designed to be kind of as inoffensive and minimal as possible. We have just barely the stuff we need to get by. It is type sound. You can have a bidirectional type system for it. And it's logically unsound, and let's just say that's for convenience for us. The real meat of the work happens in the cast language, which is almost the same as the surface language, except that we've removed the type annotation, we've added an explicit casting operator, and we have an assertion operator. So if you want to use, it's best to see it as an example, if you want to use 7 in a place that would want a bool, you would write something out like this, where 7, it has type nat, we want to use it as type bool, we know that those two things are the same type, and we have a location to this, the static place that asserts it, and we have an observation that'll evolve and give us the observations we need to track the error, if it does turn out to be an erroneous equality. Now, just for the sake of this talk, we're not going to be dealing with all of the bookkeeping, or it makes it hard to deal with all the bookkeeping if we put all this stuff in. So we're just going to abbreviate these things and ignore the type of type stuff, and ignore the location and the observation, and just assume that those are always going and keeping track of things correctly in the background. Yeah, so that seems like it might work by itself, but there are a couple things we had to do to make this actually work. So here are the sort of technical highlights. Casts and asserts can work their way into type signatures, so that's not good. To deal with that, we actually separated out reduction and blame. So this is a really convenient. There's other work that mixes dependent types and errors, and it's so convenient not to have to deal with that. So we just say this term gets stuck as far as reduction is concerned, and blame can be extracted as far as the blame judgment is concerned. Casts can block function application. And if you're familiar with contracts or gradual typing or anything like that, you'll probably see straight to the answer. But we just need to add the reductions that make us be able to apply things to casts and just do the bookkeeping you need to push things around. Finally, we have some kind of question about how we would keep track of types and equality within the cast system. So if we have some kind, this is a pretty contrived thing, but hopefully you can get what's going on here. If someone asserts and at is the same, and someone, add and at is the same, and someone gives it the inputs, where they're asserting 1 and false is the same, and true and 2 is the same, well, what type should this have? Should it be nat? Should it be bool? Should it be both? Should it be neither? How should this be considered equal? Should it be equivalent in some sense to 3 or equivalent in some sense to false? Well, we extend the typing relation to this thing we call endpoints, And it lets us keep track of the interpretation of every term in a type-consistent way. So we'll say that this both has an endpoint where it's add 1, 2 at nat, which is in some sense the same as 3, and it's also has an endpoint in and false true at bool, which in some sense is the same as false. And we're not going to talk more about these things. We're just going to pretend typing works regularly from here on out. Yeah, and we can kind of, we've extended our own kind of terminology for this. So instead of saying well typed, we'll say well cast, and we'll say things are well cast when the endpoints are good. And that leads us to our top level theorem of this, which instead of type soundness, we call cast soundness. And instead of type soundness, where well typed terms don't go wrong or don't get stuck, we're going to say well cast terms don't get stuck without blame. And the proof sort of goes along similarly to the progress and preservation proof of type soundness. Okay, now let's take a look at the elaboration procedure. And we're going to take a real distant view of this. The elaboration is basically just bidirectional type checking. We're going to just do the normal bidirectional type checking stuff, except when we would run terms to figure out when they're equal. We're just going to slap a runtime check there. And in practice, we might do a little bit of courtesy evaluation just so things don't get too messy. And this gives it a very different character than gradual typing systems. So where a gradual typing system would want to handle every untyped piece of syntax, we can handle a lot of nonsensical syntax, but not things where we don't know what the user intends to type it. So for instance, if someone has a function from bool to nat, we can give it 7, and it'll put the checks in the right place, and everything will be OK. If someone just says lambda x arrow x, well, it's not going to know what type you intended x to be, so it won't elaborate that term. So that's the functional fragment of this. And we can do a quick example of the first thing we did, which is this silly little function. And the way you get the warnings is you just read off the assertions, and you get nice little error messages, or warning messages. Now, I think it might be good to break for 1 or 2 questions, just because that was a lot, if that's OK, before I continue with the rest of the stuff. If anyone has questions, that is.
That's fine.
Yeah.
Yeah, so I'm really curious about how the elaboration works. In dependently typed languages, generally there's meta variables are used to fill in implicit parameters and so on.
We're not doing that right now. Good question.
Right, okay. So, okay. So, I was going to ask how you choose between filling in a meta variable or inserting a cast. And if you don't have meta variables, it's an easy choice.
Yeah. I have some thoughts on how you would do it, but we're not doing it right now.
Cool. Thanks.
Yeah.
I was just curious if every equality becomes a cast, or if you can.
So if there's something obvious, just for sanity's sake, we kind of, if 1 equals 1 is an assertion, we're just going to say that's fine, right? So it's kind of a heuristic thing with a limit, but so not every equality will become a cast, but we set up the theory so that every equality sort of becomes a cast. But there are some exceptions to that, but yeah.
I just have a kind of high-level question. So I know there's been a bunch of recent work on gradual dependent types, and this looks, both the language and the elaboration, the setup looks very similar. And I was wondering if you can contextualize this for me. So I know, for example, there's different design space about whether you maintain soundness or normalization, and some different choices. Yeah, so this actually awkwardly doesn't fit well into a gradual typing framework. And that's, so the work on gradual typing and dependent types is pretty interesting, but it's pretty complicated. It involves changing surface level syntax, which is not something we want to do. Though I think maybe you could say we're just gradually typing the equality relation.
To the extent that that would ever make sense, I don't. Yeah. Okay, so that was the easy story of just functions without data. But we also handle data and pattern matching, and that requires a lot of additional machinery that I'm going to quickly run through the high points of. So just to make sure we're syntactically on the same page, again, here's the surface language. Here's the data definition of that, and the data definition of length index list called Vect. And here is the function that will take a number and repeat it, and repeat something that number of times. And we're using explicit case expressions, which are made up of a scrutiny, branches. Each branch has a pattern. Each branch has a body. And there's a motive that's written out here in maybe a slightly different syntax than people are used to seeing, which tells how the branches type check in the context of the pattern. And in real life, mostly the motive can be inferred. Okay, so the surface language data works okay, but when you extend the elaboration in the cast language to handle data, you have to handle a lot of things. First of all, or two specific related things. Normal forms don't match patterns anymore. So that's not good. And also, we're using the full kind of range of pattern matching with unification to resolve things, so we have to handle unification as well. So first of all, the pattern matching syntax only makes sense because you have a head constructor, and when you have a normal form, you expect the head constructor to be there, and it links to the pattern. In the cast language, that's not what happens. You could have 0 or more casts blocking that constructor. So we're going to add a bunch of machinery that says we can always insert a vacuous cast. We can always bunch up casts together. And then we can say every data constructor has exactly one cast on top of it that we can then include in our pattern syntax. Then we need to deal with unification. And the way we're going to deal with unification is by recording the normal steps you would use to unify into the terms. And this is so we can redirect blame to the thing that caused it. So this is probably only explainable at this point through an example. Here is an expression that'll take the head of a term. And we're just going to speed past this because I think we're running out of time. So to elaborate this, we're going to take the regular constructor, we're going to take the regular pattern, we're going to insert a bunch of cast variables that will pick up the casts that will be on this in the cast language. Then we'll take the body and we'll prepare it to accept a bunch of casts that will be solved through unification. And then remember, unification is saying, well, this little a is of type big A, and we know the type of this whole cons expression is going to be that thing, and that thing we know from the motive is going to make that a bool, so we have a big A equals bool, and we can say little a is of type bool. So we have the same equality that we're capturing from the cast, and we're going to inspect it. We're going to add some machinery to inspect it, and then we're going to say we know A is of type bool according to this input we got. Then also for pattern matching, the system will synthesize the constructors that aren't there, and then use unification to show that they're impossible. For our case, it's very well possible that a constructor might show up under a bad cast, so we need to handle it. So we'll capture that. We'll add syntax that allows us to witness a direct inequality. And and that will let us redirect blame. So the important thing to notice about this elaborated term is that we haven't inserted any of those squiggly assertions. So there'll be no warnings from this code, and there can be no blame from this code. Any blame will have to come from the input. I don't think we have time for the next thing, so I'm going to run to the end. Just a quick overview of our results. We have a cock proof due to Robin, who's just did the last presentation, of an old similar system. We haven't gotten it for the new system because we don't have the patience, or I don't have the patience for it. Without data, everything works out pretty cleanly. with data, everything is kind of, we assume it's right, but it's very complicated to try to like formalize anything. Yeah, in the future work, there's a lot of, we actually have an implementation you can try, and we're so close to getting a web UI working. I was hoping we could get it this weekend, but yeah, if you're interested, we could maybe, I can tell you when it's done, maybe next week. Yeah, there's a lot more things in this philosophy I would like to investigate, where we just do fewer errors and we do more warnings. And we're actually in a very convenient place if we ever could get a user study together, because we have a language that's exactly the old way and a language that's exactly the new way, and they're exactly the same except for that one thing. Well, thanks. If we have time for any more questions.
Yes, we still have 2-3 minutes for questions.
And I'll be a little crazy. If you're watching this in the future from recording, email me if you have questions.
So I'm sorry. I'm a little confused by something you said. So to an earlier question, you said like no unification is being used, and then in the
no meta variable unification. So we don't have implicit arguments.
Okay, but aren't you introducing implicit meta variables in your elaboration?
Yes. Sorry. So there are multiple places you would use unification in a dependently typed language. We're using it in the place that is involved in pattern matching. We're not using the feature of implicit arguments or meta variables in the kind of surface syntax.
Okay, thanks.
Yeah. Thanks for clarifying.
So no more question.
Oh my god, my mind's gone blank. Sorry. I had that question in my head and it's super embarrassing. I'm sorry. I'll retract it and then ask you afterwards when it returns to me. Sorry.
Yes.
Okay, so we thank the speaker again.
Thank you. I'm going to let you do it.
So the next talk is by Peter Anukif and Earl Harley Eads. And Peter will give a talk. And yeah. Peter will combine dependent types with grids and adjoint logging for us. If you can log in. Please go ahead.
Sorry, I should have come to the technical check. Right. Hello. Thank you for being here. This is one of those papers where the title is also an accurate description of what's going to happen. So let's begin. Well, we're combining dependency grades and adjoint logic. So at this point, I mean, we've had a bunch of talks about dependent types already, but the main sort of gain is we get expressiveness, we gain verifiability, but this comes at a big price. And that is that inefficiency can sometimes be almost baked into the language. And let's look at an example of what this means. So let's consider just a very simple dependent type of vectors, of elements of some type of length n, and a push constructor which takes an element and a vector and produces a new vector. And if we look at this type, the type signature is actually not complete. Well, because we have this A and we have this N, and so they need to appear somewhere, presumably. And so we write this. Okay, that's fine. But now, what are these A and N? They appear in a type signature and they're arguments to our push, but they're unused. And then, furthermore, this is probably a functional language, so the output is probably going to be a copy. So our push function runs in linear space and time, which is not great. So we wanted to address both of these issues. And how are we going to do this? Well, for the unused variables, we're going to add grades into our type system, which can account for how variables are used, and will allow us to optimize unused variables. And then to do in-place updates, well, if we treat our values linearly, then, well, once we've used it for the push, then actually we can't use the vector again, and so it's fine to update it in place. And so that's what we did. This is our main objective, is to integrate dependent types, grades, and linear values. And this is based on Krishnaswamy et al., where they combined just intuitionistic dependent types and linear types, and furthermore, Chorir et al., which is a graded dependent type system. There are others, but we use this one as our basis because, well, my advisor co-authored that paper. So let's look at the graded type system. And this is, by the way, exactly the same as this one, with one tiny modification. So let's look at the graded type system. So we can control variable usage, and then I just wanted to give some examples of what we can actually control with this. So we can do relevance analysis like we saw before, so we can check are these variables actually used or not, and this allows us for some optimizations. We can also do automated garbage collection, so you can assign some number of uses to a variable, and then once it's used up, you automatically know it's gone, and you don't have to do any counting or anything. And then there's also things like data flow control, where you can tag variables with high or low security, and you can ensure that high security things don't leak into low security contexts. So this is our judgment form, and if you ignore this first part before this O dot sign, then this is just a judgment with assumptions and a conclusion. And these RIs here, they indicate how these assumptions are used. So R1 indicates how X1 is used, R2 indicates how X2 is used, and so on. And they are all drawn from some semi-ring R, and basically your choice of semi-ring is what dictates which resource you're tracking and how you are accounting for it. So I want to show some rules for you to get a feeling about how this type system works. So first of all, we do have weakening, and essentially this says, well, okay, so delta is the resources, this little delta is how is the resources that are used to construct this T. And then if we can introduce an unused variable, but we have to use it at grade 0, which I think makes sense. If you're not going to use it, you should put 0. We have a sub-usaging rule, which essentially allows us to say, well, if we have some resources, if we use some resources to construct T, then we can use more resources. So we can be wasteful if we so choose. And finally, this is a variable rule. Here's a variable rule. So if we have any type, then we can use the variable of that type at grade 1 to produce an identity function. And here there's actually something interesting to note. And that is this delta here references what resources are used to construct this type capital X. But this delta is gone here. And so actually these judgments do not contain any information about how the type was constructed. They only contain information about how the term is constructed. And then finally, one more rule, which is I chose function application just to see how other rules interact. And here, so we have a function and a potential argument. This annotation here says that the argument is used at grade R. So if you were to uncurry this and move this thing into the context, you would have an R here. And then, so basically this is just about showing how these grades behave. Well, we need to compute F and T individually, which explains this addition. And then T is used at grade R, so we do a scalar multiplication here. Okay, so now we introduce a mixed fragment, and this is essentially we just say, okay, we have these graded things, and now we're going to just also have linear types, and the conclusions are now going to be linear terms, and we now have this annotation M, which stands for mixed, on our turnstiles. And this behaves essentially just like ordinary linear logic. So this is just the ordinary function application rule from linear logic. And then we just also have these graded assumptions that are just present throughout all of these judgments. So this is the actual rule. And so we have a fixed context delta of graded assumptions. And the grades here are added together because we need to compute both things in parallel. So very briefly, we have modal operators that connect these fragments. These are essentially, as in Krishnaswamy's thing, except we have to make things graded in the correct way. So this F operator takes a graded term and makes it into a linear one. And it functions essentially like a dependent pair type, where the first component is graded, the second component is linear, but then the whole pair is also linear. And then for this, the other one, this takes a linear type and produces a graded type. And the terms are, in a good sense, the same, so between A and G of A. And we have a good notion that linear usage corresponds to grade 1. So now let's look back at our example. So now we can say, well, okay, this A of type and this N of type natural numbers are going to be both graded at 0. And then furthermore, we're going to make these guys here linear. And so now we have a push function, and we can correctly say that these are unused, and we can correctly say that these will be consumed by pushing, and we can do an in-place update. So from here, we have now a thing that looks like linear nonlinear logic, except one of our fragments is dependent and graded instead of just intuitionistic. And we wanted to generalize this to look a little more like adjoint logic, where we don't just have a intuitionistic and linear, but we can have potentially many different things. So let's recap what adjoint logic is. So in adjoint logic, each proposition comes with a so-called mode. Each mode has a set of structural rules which it admits. So it admits either weakening or doesn't admit weakening. It admits construction or doesn't admit contraction. Sorry. And the preorder that the modes are arranged in is compatible with this set of structural rules in the sense that if one mode is bigger than the other, then its set of structural rules is also bigger than that. So this is what a judgment looks like. And essentially, these are just assumptions. They have their modes annotated, and then we have a conclusion with its mode annotated as well. And there is a constraint which says that the mode of the conclusion has to be strictly or less than or equal to all modes of the assumptions. Now, in our system, we keep this idea of having modes that are arranged in preorder, but now we have the semirings, which account for grades in the structure. And so essentially, now every mode comes with a semiring, and this inclusion of structural rules has been replaced by having a homomorphism of semirings. So now, just briefly, I'm going to explain the judgments. The rules are actually the same, exactly the same as in the graded fragment from before. The fact that this has now different modes and that these are now different semirings actually does not answer the equation at all. I mean, syntactically, there is a notational convention, but other than that, they look the same. And so now we just, in addition to having, so if you forget about this vector of these fracture m's here, then we have the judgments from before. But now these m's just also indicate which mode the ri's are from and which mode the variables are from. And we still have the same constraint. And this is actually now important for some of the scalar multiplications to be defined. So one thing that we also wanted to do is we still wanted to gain control over contraction and weakening. And for weakening, this you can do it. Okay, so you just have a predicate that's called weak m, and okay, like if weak m is true, then you can weaken and you put 0, and it works the same way as before. But controlling contraction is actually a little more difficult, and this is mainly because of the dependency. So let's look at this hypothetical dependently typed function application rule again. So we have a function and we have a potential argument, and now we want to say we apply it and we concatenate these contexts. But the problem here is that we really should check that this little a is actually correctly of this type, capital A. And it's actually just kind of unclear what that means when they exist over different contexts. And so implicitly, well, this should just be one context, and we should implicitly contract both of these contexts together. And that gives us some implicit contraction in dependent type systems if we set them up sort of in the obvious way, let's say. And so this actually also enters with the grades, and it's unclear how to handle contraction. So on some meta theory, we actually have graded contractions in both systems, so we can actually not control it. We proved substitution for both systems, and only for the former one, we developed some operational semantics, and we proved subject reduction. And with that, I feel like I just took 5 minutes. But with that, I'm done. Thank you, and questions.
I have plenty of time for questions.
So this is a really nice talk. One thing that was a little bit unclear is about the status of contraction. Could you go back to maybe slide 25 where you talked about the problem? And it wasn't clear whether you have come up with a solution or not.
No, so essentially, if you want, sort of in the naive way, you would have these contexts both be the same.
Yeah.
And you put just one gamma here.
Mhm.
And that is sort of the reason why there's some implicit contraction in dependently typed systems, sort of by default. And that also enters for us, and so we haven't figured out a way to control it.
Okay, so this is an open problem that you don't have a full
yes, and so
solution for.
we imagine if this weren't dependently typed, we could just do it by just adding a predicate and just saying there's no contraction in this mode.
Mhm.
But now, because, well, in this case, we just can't.
Okay, thanks.
Hi, yeah, thank you. Thank you for the talk. A bit of a motivational question. You have grades, modes, and linearity. What are they used for? Like, what's the difference in? Can you give some intuition as to that? Like, why do you need all three?
So I wish I knew what exactly you're aiming for, but so.
Because they all, to me, they serve similar purposes. They're tracking how variables are used, and you can sort of use one to approximate another in a lot of cases. So that's why I'm kind of asking, what do you get from having these three of them combined? And if you don't have an answer, that's okay.
So in reality, I'm very bad at philosophical, like, motivational things. And so I don't at least have an answer right now. I'm very sorry. I come sort of more from the theory side. And okay, thank you.
I think I know the answer to this question, but I think it might help with your other one. So you used the linearity to let you, you were doing reuse, right? Or free or something similar. Like you're in your setup. Why could you not do that with why is the grading not sufficient to do that? Right? Like you have something you know that the thing is at grade 1. Why is that not sufficient to do reuse?
See, this is really embarrassing, but
I mean, I suspect
I'm sort of really the wrong person to ask for.
I suspect
for practical applications. I'm sort of I
suspect this is a distinction between linearity and uniqueness, but
okay. We have I have something. So we had a no. Here, 1, 2. We have this rule. So this is actually, so this says you can be wasteful. And so, okay, the semi-ring comes with a pre-order that I haven't mentioned, but it appears here. And so essentially, if, let's say you have 0 less than equal 1 in your semi-ring. If something is graded at 1, and you have 0 less than equal 1, then it might be used, but it might not be because it might have been obtained by applying this rule. So actually you get affinity. You get something that's affine. Whereas in linearity, you know for sure it's graded at 1. And it's really used once. And so there are some differences here. Similarly, so you get fewer guarantees. Similarly, if 1 is less than or equal to some other element, right, then you can say, oh, I allowed this this is potentially unrestricted, but it might still be linear. So you get some slightly different things from this.
Yeah, that makes sense.
Okay. I hope that was maybe helpful as well. I have like
questions about motivations.
What does the regularity property of your language look like? Because I'm just wondering, like, is there any, like, does your usage tracking also apply to the type, or is it just at the term level?
So in constructing the types, we carry these grades around, but no, the resource tracking is sort of, in this judgment, this delta, all of these really just describe how the term is constructed.
So it's similar to grad, where when you check the type, you use
it is actually exactly grad.
Okay.
We reuse the type system, basically.
Okay, that makes sense. Thank you.
I quite like the presentation you had just simply of adjoint logic in the way you showed it here. And I was wondering what your preferred definitive resource is for that version of a presentation of it.
I don't know. That's just kind of how I read that paper, and that is sort of the notes I took for myself mentally. And
from the paper that you cited earlier.
oh no, this adjoint. Oh, so there's a paper that's also just called adjoint logic.
Okay, there's a lot of papers called logic.
Oh, is there? Okay. Oh, oops. Embarrassing. Who are the authors? If only. I don't know the authors off the top of my head, but. Surely someone in the audience knows. Which one am I? Yeah, Jason. I was gonna say Jason Reed is like one of the names, and there's more, but I don't remember who they are at the moment.
That's fine. Thank you.
Yes. Yes. That's the one I'm referencing.
Could you go back to the slide with the type formation premise, where it was that one.
Okay.
So I have a question. How does this affect like the formation of equality types? Because
we don't have those.
Okay.
For now, we actually don't have any inductives for now. This is just a core type system.
Okay. Thanks.
Thank you.
The next talk is a recording.
Thank you.
Yeah. But
oh yes, sorry. Oh.
My joint work with Ning Ning Xia was also at Google. DeepMind about a new version of record types and you.
So, yeah, the talk is by Ask and Chia. So it's a recording, but one of the authors is with us, I think. So you can prepare your questions.
Record calculus with a particular focus there. Hello everyone, my name is Adam Pashka, and today I want to tell you a bit about my joint work with Ning-Ning Xie, who's also at Google DeepMind, about a new version of...
Yeah, so maybe click on speak.
Yeah, but I have lost the pointer.
Oh, okay.
My pointer?
Let's see. Can I try?
Okay, I have it.
Oh, okay.
Change the audio to what?
Change the audio source.
Settings, maybe?
Yes.
Sound?
Yes, sound. And then there should be output device.
HDMI?
Yes, no, I'll try it.
Okay. So we forget about...
collaborates with us, and so our group actually mostly focuses on programming with multiple.
So we are using the Zoom solution. Otherwise we don't have audio. Are you ready for the plan? Plan B? No? Yeah. How many PhDs do we need to start a video?
Google DeepMind about Hello everyone, my name is Adam Pashka, and today I want to tell you a bit about my joint work with Ning-Ning Xie, who's also at Google DeepMind, about a new version of record types, a new record calculus with a particular focus on typing and analyzing tabular data analysis. So just to give you a bit of a background, I'm in a team that works on a numerical computing library called JAX that is embedded in Python. and Ning Ning collaborates with us. And so our group actually mostly focuses on programming with multidimensional arrays. But, you know, we also like to sort of sometimes think about other things. And tabular programming always seemed very close and yet like a little different than multidimensional array programming. But we figured, you know, we want to think about this more. We do like type systems. We have another research project in a research language called DEX, which, you know, where we essentially designed a typing system especially for multidimensional array programming. But at the same time, having, you know, designing a library in Python, we do actually understand a lot of our users wouldn't necessarily agree and they wouldn't want to have an overly complicated type system. But at the same time, we do see a lot of users wanting, you know, static analysis. They want to see how the shapes of the arrays and their data progress and the types change as they write their analysis. So the question here is, can we design sort of a lightweight system that will allow us to answer those questions and do a very lightweight formal verification of essentially code that operates on data frames? So now, one interesting project here, as I mentioned, we're not experts in data frames, but there is the Brown benchmark for tabular types, which is a very interesting development. It essentially summarizes a number of scripts that have been put up online that do data analysis into essentially a little benchmark for what kind of tables you should support, what kind of functions that manipulate tables you should support, and what kind of errors you could be potentially catching. So this is what we will use for evaluation at the end. And so as a starting point, we took, you know, essentially what we kind of consider a bit as the archetype of a table language, which is SQL. And the first thing you do in SQL oftentimes is you create a table, right? And if you look at what you specify when you create a table, it's essentially a collection of heterogeneous fields that you can access by name. And if you translate this to the language of type theory, perhaps that starts looking very similar to record types. And so that's what we ended up looking at. But one conclusion we ended up with is that actually a lot of the record theories either end up a little too constrained or they end up being very complicated, perhaps with an extensive use of qualified types that we feel just would be a little difficult to explain to users. And it might just get a bit in the way of you know, them successfully just writing some program to summarize some experiment. So to summarize this talk, there will be 3 parts. First, we'll go over an informal sketch of our calculus. Then we'll go over the formal definition of our language and the formal results. And finally, we will see the evaluation section to see how it does on the Brown benchmark for tabular types. So we'll start with the informal sketch, as I mentioned. In the first step, you can think of records essentially as sort of tuples with named fields. So in here, you can see a record type. It has 3 fields, length, height, and width. They all have the type int. Now, at this point, the only record operation that we really care about is projection by name. Notably, you cannot project by position, and that is because we identify records up to field ordering. It doesn't really matter in which order you declare the fields in a record or in its type. They can be freely permuted, and they will be considered equivalent. Okay, so next step is to allow something similar to structural subtyping. This is a very standard calculus for records at this point. The idea is that now you not only are able to declare the sort of fields and types, but you can also say, and then there is a row. So essentially another sort of set of fields in the record that you will just completely ignore in your polymorphic functions. And this allows us to, for example, apply area to records that have height and width, but then of type int, both, but then also like an arbitrary suffix of other fields that get ignored. Now, there is an interesting question, though, which is what happens if this polymorphic tail actually gets instantiated with a pre-existing field name? What if the row here actually does contain the field width or height? And so usually what most record theories do at this point is they will reach to qualified types to essentially encode constraints such as the extension cannot contain height and it cannot contain width. Now, we didn't like that very much, and we found a solution in one of Dan Leyen's papers. And that is to allow scope labels. So essentially records now do allow duplicate labels. As you can see here, the record has duplicate field L, but the fields shadow each other. So now the order starts to matter a little bit. When you project L from record like this, you get back the integer 2. To access the second field, you actually first have to delete delete the field L from the record, which will remove this one, only leaving a record with this component, and then as you project L again, you will back the field of type string. This is a valid program. And again, as I mentioned, records are not completely unordered anymore. The fields of distinct names can still be permuted freely, but within a single name, the order of fields matters because it does change the shadowing. Okay, and the next extension is first class labels and rows. So essentially what we have found is that it's also often useful to be able to treat those names as first class values. You want to write a function where the user says, get me a value of this column, and the column name is passed as a value. And so this is essentially what it is. We're adding singleton types for field labels and for record rows. Now, one nice property of this is that record field projection can be assigned a proper type. You can see that here it essentially is a function that says for any label, for any type alpha that this field will have, and for any row afterwards, if you give me a record that has this field L of type, which we will discuss later, I will give you back the sort of value of that field, which will be of type alpha. Now, an interesting problem arises again. Consider this function here, which says if you give me any label and then a record that has a field of that label in type string and then a field of type foo of int, and the program essentially just accesses foo from that polymorphic record. The question is, what will be the type of that? And in our theory, we actually reject this, right? And this is because if L gets instantiated at foo, the type should be string. But if L gets instantiated anything else than foo, then actually the type should be int. And so that's why the program is rejected. We kind of cannot infer that statically. If you really wanted to access the field foo, you would have to do what we did before. So you would have to explicitly first delete the field L and then access foo. So essentially an interesting thing here is that essentially first class fields, once you do allow scoped labels, and to the best of our knowledge, this might as well be the first place where this is done, you do have to consider those first class fields with first class labels to shadow all of the subsequent fields, because you kind of cannot reason yet about their shadowing semantics. And so that constrains even more the permutations you can apply to record fields. Okay, and finally, the last operation we add is record concatenation. So you can essentially take two records and kind of splat them together, all of their fields. The interesting part is that now you can essentially write records that arbitrarily interleave extensions with rows and with labels and with fields where the labels are first class or just literals. And another two interesting operations are perhaps row projection, which essentially just restricts the record to one of its sides. So you essentially drop a bunch of fields. Okay, moving on to the second section, we'll now discuss the formal results. So in here we have defined essentially a model language, which you can see here. Essentially in the first row, it's just fairly standard lambda calculus with let bindings. In the second row, you can see the record constructors, you can see the label singleton constructor, and the field projection operator. In the third row, you can see the row constructors, you can see the row projection and sort of deletion from the record. Now, since we've based this on essentially polymorphic lambda calculus, the type system we specify is an extension of the Hindley-Milner style polymorphic type system, which for most of the language is standard. We do specify the rules for all of those new constructs, although they are not that complicated. The two most interesting parts, I think, is that we had to add this rule, which essentially lets you cast the type of a term to another type for as long as they are considered to be equivalent under this equivalence relation, which basically says, again, they might differ by permutation of the fields in records for as long as they are valid, right? So it encodes things like concatenation of rows is actually an associative monoid. It's just a monoid, and empty row is the neutral type. And also, it encodes the details of field shadowing and when they can be reordered. The second interesting rule is the variable rule, where you would have to, if it has a sort of polymorphic polytype, you might need to instantiate it. And so we actually restrict the instantiation a little for variables that correspond to labels or rows. And so if you take this as an example, so E is an expression of type for any label A, it will give you back a record with a field labeled by A of type int, and then L2, which is a literal of type bool. And now you can ask what will be the type of E.L2. And the problem here is that depending on the instantiation of A, you might end up answering int if you instantiated A to L2, or you might end up with bool if you instantiated A to anything else, right? So we essentially constrain instantiation to only allow instantiating variables that allow in sort of the tail position of the record. Again, for more details, I unfortunately have to redirect you to the paper. Okay, and the final component of the formal part is the type inference algorithm. We do extend a Hindley-Milner style type inference scheme. We show that our type inference procedure is sound. We do discuss that the system actually lacks the most general unifiers. This has been a known problem that's also discussed in the paper that introduced scoped labels. Essentially, already at that point, you start losing that property. You can see that if you try to unify, a row like this with a row like that, you can sort of use this component to unify with this and that with the second part, or you can swap them. And since L1 and L2 are disjoint labels, both will give you valid solutions. Now, as a silver lining, when inference does succeed, we actually do show that it does return the most general unifier. And sort of very practically, we in our evaluation, we actually haven't found any cases where that would be a problem. And that's probably because actually this unification problem is very unnatural from the point of view of our system. It can happen, but it's very unnatural, right? And that's because to instantiate the inference variables alpha and beta, beta is okay because it's in tail position, but recall the tail check, we normally would not instantiate alpha at the front. So that usually only happens when there's another argument, such as an explicit label, that would specify alpha, and essentially given that label, inference would still have enough information to succeed on this program. All right, we get to the final evaluation section. As I mentioned, we will be looking at the Brown benchmark for tabular types. We evaluate our solution on we don't have a concrete implementation. We have a very early prototype, but that was way too early to put in here. So we evaluate assuming a Haskell style language that is extended with our record type operations. In particular, we assume existence of some types like maybe, and then arrays or list types allowing arbitrary types inside. And we will not be talking about implementations of methods since this language is entirely hypothetical. We will focus only on the typing discipline. So, okay, so tables, this is the first step of the benchmark. As we mentioned before, a table is essentially an array of records. Now, one big deviation from the benchmark, and a requirement we fail, is that the benchmark does require columns to be ordered, which they're not here, and it does require them to be unique, which again, they are not. Column shadowing can potentially lead to bugs, but we still find it as an acceptable sort of trade-off, given that we can essentially end up with a significantly simpler type system. And here you can see the types of the tables from the benchmark, but unfortunately I will not have the time to get deeper into this. Here is a summary of all the functions except for the functions that only modify rows, like permute the rows of a data table, for example. Those have nothing to do with columns, and so with our record types. So here we only focus on the ones that actually are relevant. You can see that for most of them, we actually do succeed to do pretty well. There are some exceptions, like for example, get column, in the benchmark it should also work in positional indexing, and here we can't. Rename columns, for example, it can let you rename multiple columns at the same time. In our case, we can only type a version that renames a single column, but luckily renaming multiple columns, you can just get it by composing the function that renames a single column multiple times, so hopefully it should just work. One interesting example, just to give you a sense of how this works, is left join. Essentially, a left join, if given a table, two tables like this, what happens is that it sort of takes the left table unmodified, and then it looks at the key column and here ID, and it tries to look up the values in the right column. If they are there, then it just puts them in the extra column. If not, they are missing. Now, we cannot just type this directly because we don't allow missing values in arbitrary places, but you can see from this type that you can actually resolve this fairly easily, right? You have here the one data table with the key columns and value columns, another one with key columns and other value columns. You specify explicitly what the key set of columns should be, and then in the result, we just copy the left record as it was, and then we attach an extra field, which is an optional value of all of the value columns from the second record. Okay, and about static reasoning and error checking, essentially all malformed tables that the benchmark lists are rejected by our systems. When we looked through the example errors, most of them were because the programs were accessing columns that just didn't exist, and in our type system that is also caught. Array length checks are kind of independent, so again, depends on your array type. And again, disjointness constraints cannot be enforced. But I think still, like, we want to stress that, you know, checks are an added thing here. I think just the most important part is that we can track the progression of the shape of the data. Finally, just to quickly discuss the negative results. So one group was table pivots. That's essentially a group of functions that take a number of homogeneously typed columns and flatten them into two columns, one with column name and another one with value. That's kind of a complicated operation to type, and we didn't find a sufficient solution here. Outside of the benchmark, there are also a few interesting points. One is about type classes for records. Sometimes we would like to do record equality, and there is a question of whether we can integrate this into existing type class systems. Records are not really built inductively, right? Because there are multiple potential definitions, because, you know, field ordering doesn't matter that much. If you're interested, please do please do take a look at the paper. Schema reflection is another one. Can you get a list of labels of columns? Right now, we don't have a great answer for that. And finally, I do think that there are some limitations of using singleton types as, as sort of calling them first-class labels or rows. I do think that they are still fairly limited, but again, due to time constraints, unfortunately, I will have to skip that discussion. Okay, just to conclude, we did present a novel record calculus, which essentially combines a lot of existing features, adding a few more, but the combination itself is, to the best of our knowledge, unique. It can successfully track the evolution of the shape and, you know, type of the table through different data table API functions. It does fairly successfully verify the invariance mentioned in the benchmarks. It is I would claim, obviously it's subjective, but I would claim this is still a fairly simple type system. There are no qualified types necessary and constraints. But, you know, we still don't have a practical implementation, mainly because some questions remain unanswered that are important in practice. That's everything I have prepared for today. Thank you for listening. And if you have any questions, feel free to ask them now or reach out to me under that email. Thank you.
Hey, Maxon, BCA Research. I work with APL, the array programming language, and one big feature I enjoy is rank polymorphism. Are you familiar with that idea? And how do you have any plans to implement that? And if you do, what are some of your ideas?
So currently we don't have like an implementation, but like this is like part of the future work we want to do in the future. Like maybe APL would be like a good target language to do that. And I would also like to comment, like in this work we focus more on like column manipulation operations, like where like you try to like get a subset of the database. But like we do not focus on like row manipulation operations, which I think we will need facilities like dependent types and like array programming, more like functionalities from like the APL language. So maybe there is like a good, it would be like a good interesting piece of like future work to like try to combine like the row features with the column features, and to have like an implementation, a proper implementation of our system in languages like such as APL. Yeah. Thank you.
Test. So just one question: the left join operation in the benchmarks. So are you? I wasn't clear. Are you presenting the type, and that would be a primitive operation or something, or do you also have an implementation of left join in your calculus?
Right, that's a great question. So we do not have implementation of our language, but we try to give a type signature of all the column manipulation functions from the benchmark, just to see like whether we can actually give it the proper type using our type system. So the type signature for left join is like one example where like we would need to slightly change the type signature or like the type signature from the original benchmark to make sure like we can deal with like nullable like fields, which are sort of like people take for granted for languages like SQL, but it's not like properly typed if you actually want to have implementation with a proper type system for it.
Hi, Ning Ning.
Hey.
I did a comment on the question about rank polymorphism. I think there's a difference of terms. You're both talking about arrays, but you're talking about different kinds of arrays. So APL kinds of arrays, where rank polymorphism is important, does transpose work for your kind of array? Whereas the data frames kind of array, which I think you're more into, is not the kind of thing for which you would transpose and so on. So I think there's just a terminological difference there. Is that fair? Let me turn it into a question. Is that fair?
Well, I'm not exactly sure. Like I understand like what rank polymorphism means. Probably like in languages like APL, where you can deal with like arrays of different shapes, like for example, and and I guess like having a proper like array type like is not a focus of like this work. So it's like we can probably like integrate our type system with like a type system for array programming, whether or not like with rank polymorphism. I think that's what I was trying to say.
So data frames are kind of inherently two-dimensional with column headers and things in the columns.
You can have like nested tables.
Okay.
Right.
That's not quite the same as a three-dimensional thing.
I guess so. Yeah, there might be some like interesting questions like that people can answer in this domain.
Thank you.
Thank you.
Thank you for answering the questions.
1, 2, 1, 2. Okay. All right, I think we're about to start. So welcome everyone to the first afternoon session of TyDe. We're about to hear 4 talks, all very interesting extended abstracts for this year's TyDe. And the first one is Ayumu Saito, who will tell us how to define a intrinsically typed probabilistic programming language within a theorem prover. Ayumu.
Okay. Thank you. I would like to talk about an intrinsically typed probabilistic programming language in Cog. First, I explain about motivation and contribution. Our first motivation is symbolic evaluation of probabilistic programs. For the sake of explanation, consider an example. This example means that whether today is a weekend or weekday based on the number of buses passing by. The program involves several key steps. First, sampling whether it's a weekend or weekday using Bernoulli distribution. Next, setting the number of buses passing by during 1 hour based on the value of x. In the weekend, 3, and in weekday is 10. Next, evaluating the likelihood of observing 4 buses passing by, assuming a Poisson distribution. Finally, normalizing to ensure probability sum to 1. The issue here is how we can formally prove that this program corresponds to the intended distribution shown in the slide. Our second motivation is the proof of transformation of probabilistic programs. Consider the commutativity of let-in expressions. This lemma shows that swapping the first and second line of the code does not change the meaning. This equation holds under the condition that x is not free in E2 and that y is not free in E1. This is a non-trivial property relying on Fubini's theorem for S-finite measures. The issue is how to turn this property into a formal lemma. About these motivations, we made the following contributions. We provide a formalization of SFPPL. SFPPL is a first-order probabilistic programming language, and its semantics uses S-finite kernels. Kernels are essentially functions that return measures, and S-finite kernel is a class of kernels. And S-finite kernels have a good property of being stable by composition. This stability is used to give a semantics of let-in expressions. More specifically, in this presentation, we make 3 technical contributions. First, we provide an intrinsically typed syntax using canonical structures and custom entries. Next, we introduce a denotational semantics for SSPPL. Finally, we demonstrate practical applications in symbolic evaluation and program transformation. First, about intrinsically typed syntax in Coq. For the sake of simplicity, we will temporarily introduce a language focused on the basic element of functional language, called a TyDe language. The type is U for unit and R for real number. The expressions is element of type U, R for real number, X for variables, plus operator for addition operations for only real numbers, and let bindings. The context is defined as list with list, not as a set. Then the typing rules is here. TyDe is for the element of type U. R should be real numbers. The variable X is variable X is typed to the type that is paired with the first X in the context. Addition for only real number. In letting expression, the environment is extended by X typed in A. We formalize the basic types U and R as an inductive type and define a context as a list of pairs of a string and of a type. With intrinsically type syntax, the expressions are defined by an inductive type, indexed by a context and a type. Basically, it is defined according to type rules. The lookup in the variable expression is a function to find the type of X that first appeared in the context. A lookup is computed when you take a ground string. We encounter an issue when encoding expression like this code. The problem arises when we try to construct such expressions using the inductive type. Inductive type without an explicit intermediate context. We need to give outermost context. We do not give a type because it is intrinsically typed. We expect Coq to compute the intermediate context using the proof of equality E level. Unfortunately, the abstract syntax tree does not type check. Example and error message are shown on the slide. Looking at error message, it looks like Coq does not exploit all the available information. We solve this problem by improving unification using canonical structures following Gonsier. There is some boilerplate. First, we define a structure that incorporates a tagged context and a proof of the unification problem we want to solve between a context and a type. We define aliases for tags to control the search of a solution. Coq will first look for a solution with a found tag, and it fails, it will backtrack and for definition and look again for a solution with a recurse tag. Last, we declare canonical instances for the unification problem. Found tag corresponds to a variable at the head of context. Recurse tag corresponds to a variable in the tail of the context. We show in the next slide how to use this boilerplate. Redefine a variable expression with a fine structure instead of a context and a proof of equality. For fine structure f, context of f is the first projection, a context, and context proof f proof f is the second projection and equation. Sorry. Example letting out is fixed as follows. We use x bar prime instead of x bar. We put a 4 instead of e level. 4. This 4 will trigger unification. The structure is automatically inferred and put in place of the whole. Next, I talk about the syntax and semantics of SFPPL. First, I show complete syntax of SFPPL. About types in addition to the type of toy language. Type B for bool, type PA for distribution over A, and product type. The expression defines the necessary constructors and gives a distinction between deterministic and probabilistic. Similar to toy language, context and type as indices, the distinction between the deterministic and probabilistic is managed by a flag index. We illustrate the syntax with constructors for probabilistic expressions. We display informal typing rule and its encoding. Sample is a probabilistic expression. It is encoded by type XPGT. Its parameter is a deterministic expression. It is encoded by the type XDGProT. We see that the syntax encoding embeds the typing rule. The encoding of score is similar to sample, except that it is an expression of type unit taking as parameter an expression of type real. The encoding of normalize is like sample but other around. It takes a probabilistic expression and returns a deterministic one. The semantics for type R is the measurable space for reals, taken from the mass comp analysis library. And the semantics of the Cartesian product A1 times A2 is the product of measurable spaces, also taken from mass comp analysis. And semantics of PA is the set of probability measures with an appropriate generated sigma algebra. The semantics of context is an iterated product. The last U is for unit when context is empty. Semantics of deterministic expression and context gamma with type A are measurable function from the semantics of gamma to semantics of A. And semantics of probability expressions are S-finite kernels. Next, we consider formalizing the relationship between syntax and semantics. Functions correspond to deterministic expressions are defined as deterministic values, and S-finite kernels correspond to probabilistic expressions are defined as probabilistic values. We describe the relationship using mutual inductive. For deterministic, come with a proof that the function is measurable. For example, let us look at evaluation of variables and return. The semantics of the variable expression is essentially a function that accesses the environment to retrieve the corresponding value. First, we compute the index of the string variable in the context G. Archetype is a generic measurable function that accesses the environment appropriately. Measurable archetype is the proof that archetype is indeed measurable. The relation between the syntax return E and the semantics let us assume that E evaluates to a function f. Where let f is the Dirac S-finite kernel corresponding to f, built using the Dirac measure. In practice, it is desirable to define it as a function rather than as a relation. So we prove the properties of left totality and right uniqueness. By using left totality, we were able to define exec T and exec P. As function exec P as functions that return measurable function and S-finite kernels. Exec T is shown here. A measurable function is a dependent pair of the function and a proof that it is measurable. Next, by using right uniqueness, it is possible to prove that exec T has the same correspondence as evil D. And it is guaranteed that it behaves correctly as an evaluation function. Next, application example. State and bus example shown in the first slide could now be described as this. We use custom entries here for readability. We want to prove that the execution of this syntax is equal to the intended probability measure. Exec p let in transposes syntactic let-in into notation using semantic let-in. This let-in, semantic let-in. And since the let-in expression appears 3 times, it can be applied 3 times xp let-in, like this. Next, exec sample can be similarly rewritten. By repeatedly rewriting the exec expression, we were able to form it into a semantic form. Applying semantic rewriting rules finally is such a measure. Here, \d stands for the Dirac measure. Finally, conclusion. We propose an approach to intrinsically typed syntax in Coq using canonical structure and custom entries, and denotational semantics for probabilistic programming language, and for formal reasoning about probabilistic programs. Please see this link about future work. So, especially contribute to mass comp analysis to support more distributions. Yes, thank you.
All right, thank you very much, Ayumu. We have time for maybe one quick question. Yes, Pierre. Let me.
So a quick question then. There was some trouble with defining the tags, differencing the tags. Why not use De Bruyne indices instead of having to deal with strings and canonical structures? Was it?
Oh.
Oh, that's fine. If it was just a design choice like that, that's fine. Just curiosity.
Sorry, I have no idea.
That's fine. We can take it offline. Don't worry. So all the x's and the y's that you have to do the canonical structure to find them in context.
But even with the prime indices, you will still need to go to the context to find the type corresponding to the index.
Mm-hmm.
So maybe it's moving from strings to natural number of indices won't change the way that the is not solved.
Okay.
The mapping between string and indices, it's maybe easier regarding prime.
Okay.
All right, let's take the discussion of, precise discussion of representation offline. I will be interested in looking at that too. So let's thank Ayumu again.
Hello?
Okay.
It works. Oh, great. Thanks.
All right, brilliant. And the second talk in this session is by Wei Shi, who will tell us about the type system for feature engineering.
Yeah, thank you. If I can find my mouse. Where's my mouse?
The other screen, possibly?
It doesn't move to the other side. Oh, okay. So that's the left one. Great. All right. So my name is Wei Xi. It's great to be here. So I'm gonna present a work that we have built at Meta. So basically, we built a small compiler for kind of a SQL-ish DSL, and so for feature engineering. So basically, what we have built is rather straightforward. But what's interesting is the context, like how do we use the tricks from building type theory for feature engineering. So let's start from there. So I guess for everyone in this room, when you see this title, the response will be, huh? What on earth is feature engineering? So let's start with that. And for the people who actually work on feature engineering, their response will be totally different. Well, what on earth is a type system? Well, what it does? So we will go in, maybe we'll spend 1 minute on that since everyone knows what's it. So let's say I'm going to teach Agda to some undergrad students, right? So maybe I want to write a machine learning model to predict how well received my class will be. So basically what this model is, well, if this person may like Agda, so this is a model and you need the inputs for the models, right? So you're going to come up with some data, like how about maybe the line of Haskell programs this person has written, or the number of induction proofs, or maybe if this person fancy Unicode because it doesn't exist in Haskell. And so anyways, so these are kind of the inputs to this model, and we call them features. So that's a fancy way of saying models, inputs to models. And so what is feature engineering? So maybe if I'm a domain expert of say teaching dependent types, I may realize, well, probably the number of Haskell programs written and the number of induction proofs written are kind of the similar thing. So maybe before I feed them into the model, I may want to add them together, use as a one number, so that my model may perform more efficiently or more accurately. I don't know, but that's the idea, right? So that's feature engineering. And so basically it's just transforming data. And so it's a SQL-ish language. And so in this talk, I'm going to cover just a very handful, like 3 operators, but it's going to give a meaningful example of what we are doing here. So the first is, so we have a table, right? 3-person, X has written 100 lines of Haskell, Y 42, Z is -10. So yeah, how can it be negative? Maybe they wrote too much Python or C++ and whatever. Yeah. So yeah. So the first operator is very straightforward. It's just adding a new column. Column called this number is divided by Haskell by 2. So we are adding a new row here, a column here, and so that's add. So see, basically the entire DSL is like this. You have operators, and this operator you can just embed some, let's just say ordinary lambda expressions. So it's the operators that are interesting. And the second operator is filter. What it does is to manipulate with the row numbers. So if I just want to ignore everyone who has negative number of Haskell written, I just filter Haskell larger than 0, and this unlucky person is gone. And right. So and what's the most interesting one? This is covered in the talk in the early morning one. It's called left join. So what it does is it takes 2 tables. So they may have something in overlap. So maybe the names XYZ and these names. So they may not be completely overlap. Like you have X in the first table, but not in the second table, right? So when you do this left join, there's some magical semantics happening. That is, every row from the left parent will be preserved. So you see XYZ are all here, and from the right parent, only the rows that match the condition will be preserved. So so because we are checking the equivalence of names, so you see W does not exist in the first table, so it's gone. And and on the other hand, this Z here, it doesn't have a correspondence in the second table, so it has a none. So basically everything is a kind of a maybe type. So that's the 3 operators, and that's good enough to show what feature engineering does. And okay. And now, so just like ordinary programs, there are many different ways to write the same feature. So if you think about semantics, what left join does is to preserve everything from the left parent. So if you have a filter on the left parent, then it's perfectly safe to move it below the join operator, and it's the same program. You compute to the same table. So that's kind of the equivalence, and it's kind of the crux of the matter. And okay, now what is the problem? So we have looked at this kind of the smaller picture of feature engineering. That is how one person, say one engineer, may write a piece of program. And what about everyone in the company? So there are a lot of problems. So our work started by the third author asking me this question. Hey, VC, can you use your type system to do semantic validation? Back then, I didn't know what on earth is semantic validation, and I said yes. So because I have faith in our type system. So turns out to be, here's the more elaborated description. That is, so we have a compiler, right? And you see we can move this filter around, right? And so one particular thing about this compiler is we are compiling to different backends. So maybe one function runs more efficiently in one backend, but not the other. So we need to change the shape of the graph. And we need to validate if the transformations we are doing is correct. We're not like accidentally dropping rows. So that's the first challenge we were facing. And the second thing is preventing duplications. So something very particular about our compiler is we do not compile only one program. We compile like 100,000 programs simultaneously, kind of global. So one interesting thing is how do we find duplications? Because do you really have 100,000 different ways to compute different features? Probably no. And so if we can cut down the duplications and probably merge the same nodes in the graph, we can save a lot of power. So that's the second problem. And the third kind of problem is we want to build a queryable kind of data. That is, if we have that many features and we need to check, say, privacy policies or some regulations, or maybe you just know if a feature contributes to the revenue of the company very much. So we need to query those features over and over. And it's just impractical to just run that 100,000 features every single time, because everything may have like hundreds of nodes. So that's difficult to do. So those are kind of the problems we are facing. And so far we have used this type system to solve the first problem. We are working on the rest too. So let's look at how do we do that. And so that's kind of the background for feature engineering. And for people who don't know type system, and so if maybe not in this room, maybe someone's listening on YouTube, maybe my colleagues. Anyways, so basically type inference is you have a program like 42 and you generate a number like int. So that's kind of the simple type. And if you have dependent type, things becomes a little bit more interesting. Say if I'm appending two lists, the first list is empty, the second one is just 1, 2, 3. And so of course my type system gonna tell me, well, it's a list containing ints, there are 3 elements. But if you have built a, say, dependent type language, then a trick that you often use is you're gonna store the normal forms or kind of the intermediate states of your program, because like this 1, 2, 3 is the normal form of empty list appending to 1, 2, 3, because you're gonna use it over and over. And so the trick is in our type system as well, types are actually data types plus the normal forms. And so let's talk about the normal forms. And so normalization by evaluation, that's the core of our little type system. So the idea of normalization by evaluation, I'll go over it very quickly because probably everyone knows it. If you have different ways of writing expressions, like double applying on 21 and any other way, and they will be reduced to another domain, maybe a value called 42. And then you read this 42 back, so you now map many different expressions to one unique expression. And things can get a little more interesting when you have variables and binders. So maybe you're gonna do some variable elimination or called alpha equivalence using the Brown numbers or one way or another, and maybe you can do some swapping of the order. So that's the general idea. And now let's go back to this feature engineering problem. So we have this very simple grammar. We have, let's say, 3 or 4 operators, and we have some expressions. So here's what we did. So basically, let's say we have a table. We have 2 tables. The first table has names and the number of Haskell programs written. The second table is names and the number of induction proofs written. Right. So I'm say filtering out the first table on people who has positive number of Haskell programs doing a left join, and I'm adding the number of Haskell and the number of induction. So as we just went over before, there are 2 ways or many different ways to write the same program, because you can move this filter node around. So and now the problem is very straightforward. So we have 2 different graphs that may be seemingly different, but they can be type checked or type inferred to the same type. So here is the type. It consists of 3 parts. One is kind of more conventional, ordinary data types, 3 fields, string, integer, and integer. I mean 4 fields. And the second is about the conditions. Because in the SQL language, what we are doing here is, well, we manipulate the row numbers. And so basically what we had done is to design kind of a value form for the SQL expressions. And so when you have a filter, you are reducing row numbers. And maybe when you're doing a join, you have some condition here. You are doing some kind of another conditions. So we are doing a normalization on each expression of this filter and put them in this K or kappa for conditions. And the third one is row. I choose this letter row because it's like when you're writing an interpreter, row is an environment. It captures the computation of every variable in your visible scope, right? So, and this environment here, it will kind of normalize every added variable like x here, all the way to all the functions it has went through, all the what's that? Operators it has went through, and all the way to the table. Like here, let's say that look at this induction here. That's an interesting point. So here, because it's from the right parent of a left join, so some rows in this induction will be lost. And so what we're doing is just simply adding a tag, saying, well, there's a join. So now we know this join on induction is different from induction itself. So that's kind of the result. And let's say if we have another join, maybe a right join, which is different from the left join, because in a right join, you're going to preserve everything from the right parent, but you're going to lose something from the left parent. Now, these 2 programs going to compute to 2 different types, because if you normalize the filter node, the first one, you have the row loss after the lineage, after the filter. So if you look at the lineage of induction, it's just from the original table. It's saying nothing happened to the original table. But if the filter node happens after the right join, and then you can see this tag here, so they will be different. And so, okay, so yeah, that's the idea. I guess so. Before most work on type system is designed for humans, like how do you catch more bugs? So maybe another perspective is, well, maybe you can use it to for the machines to detect more things. Okay. So to quickly sum up, we designed a kind of a type for the tables in a SQL language, particularly for feature engineering. Consists of 3 parts: the data types, the conditions, and the environment or the computations. And so here's a example of the inference rule of this filter. So if I'm filtering this table T0 on some condition K, So first off, this table itself has a type, a triple, types, conditions, and environment. And then this K got to be a bool. So as a result, we are kind of evaluating or normalizing this new condition here, adding it to the original conditions. So that's filter. And for life drawing, it's kind of similar. And we have many operators, like 20 of them. So if an operator somehow impacts the row numbers, we're gonna just add a tag to all the computations that it involves, so that we know, well, this one is changed. Right. So I guess that's it. Thank you.
Thank you very much, Wei Shi, and we have plenty of time for questions. So.
So first a remark. You said what if we were using types for machines? Actually, historically, I mean, Fortran was designed with types so that the compiler could produce faster code. So I mean, it's not crazy. Now for the join attack, so I see what you're doing. In a sense, if I were doing this in independent types, and it's actually a traditional issue, right? If you have a filter function over vectors, so vectors list indexed by the length, you apply a Boolean predicate over the elements in the list, then what's the type of a resulting vector? We don't know. So we put an existential, or we do. So join here seems to be playing the role of an existential. There exists some size of table, but then it doesn't name. So are you using it for something in particular, or are you hoping that when you see this join tag in your types, you can do something clever?
So for now, it's only to differentiate a column that being joined, being impacted by join, or not being impacted by join.
All right.
Yeah.
Okay.
But yeah, that's an interesting point.
Okay, thanks.
Yeah. Okay.
Any other questions?
So you mentioned at the start that you said you had 600,000 programs or something that you were trying to compile down.
More than 100,000.
More than 100,000. Sorry, the number anything more than 10 is pretty large. Why do you end up with such a large number of programs?
I don't know if I.
Oh, you're maybe not allowed to say.
Yeah.
That. Oh, sorry. Okay.
I guess when I joined, there are already that many joined the company. It's, I guess in real engineering, it's very difficult to control everything, and so.
Okay, so it's some sort of optimization process over the top that is generating these different candidate programs or something like that.
Yeah.
Okay. Okay, cool. Thanks.
So I guess I'm just wondering, so since we're sort of doing like feature engineering here, I'm wondering where in the process of engineering would you want to use this sort of program for doing these kind of things, I guess?
Oh yeah. So it's kind of okay. So about feature engineering, it's like this. There are some we call ranking engineers who write SQLs and throw them into machine learning models, and they invoke the compiler. So during the compilation, we're gonna capture, we say, the semantics or this triple of that feature, or some important nodes of that feature. We're gonna store it physically somewhere. And and then if someone else writes another feature, we're gonna kind of run a query to detect whether this feature already exists. If this this triple is already there, so that's basically what we are doing. And that's about authoring features. And there are some other mechanical processes, like we want to query, say, the value of each feature, and that's also that's an external process.
I see. I'm wondering if so you have sort of a database of features, I guess you would say.
Yeah.
And so I guess there's like some data describing like
Exactly.
where it came from, right?
That's a really good point. So actually, one thing we are building right now is kind of trying to build a relational programming language, I don't know, or similar. So like you can query it like in Facebook, there's a open source library called GraphQL. It's a kind of relational programming language. So what it does is maybe I have a feature name and I want to query, well, what are the fields, what are the table fields it's using, right? So that's some relation, and other kind of relation is something like that.
Yeah, it sort of reminded me of like when your first example where you had like the sort of the symmetry like thing, and kind of reminded me those programs back when they would just like you would like run this sort of like I guess like entropy program, and it would like find like the symmetry that best sort of matched the based on
exactly.
some sort of principle, right? And so that's what it sort of reminded me of, and I guess it leads into the question of like a lot of these like programs, it's sort of hard to I guess decide how it's equal. Like say like you're using like some machine learning algorithm, right?
Mm-hmm.
How can you know if they're sort of equal? I guess is what I'm trying to I guess understand. Like I'm not really sure if it's relevant, but I guess I'm just sort of wondering how you would put like a sort of program like like a neural network, for example, where it's kind of hard to compare and stuff like that. Like I guess is what I'm trying to ask.
Yeah, that's a really good question. I guess our first step will be just building a database and storing everything. And neural network is not a bad idea too. Yeah.
All right, let's continue this offline, please. And Jacques, do you mind getting set up? All right, so while our speaker is getting mic'd up, let me introduce him. So the second half of today's session seems to be a little bit themed, since both talks will have something to do with quantum computation. And the first of these will be soon enough. No worries. All right, so if you could just get mic'd up real quick. All right, so the first speaker is, or third speaker in the session, first on quantum computation, is Jacques Garrigue, who will tell us, well, how to understand it in a type theoretic sense, so that we can finally make sense of it. Or maybe just me.
Okay, so let's go. I'm going to talk in this order, basically. So introduce what is the unitary semantics, because we are going to talk about pure quantum computation, for which the standard approach is to give an unitary semantics. And then the next steps will be more specific to our work. First defining the notion of direct power vector space, and then through lengths and currying and uncurrying through lengths we can focus, and then we can prove circuit corrects using this approach. So what about the unitary semantics? So this is a very short introduction to the what is the unitary semantics of quantum programs. Basically in the unitary semantics, the idea is that rather than having a qubit, normal bit will be a value of 0 or 1. A qubit is actually a vector of norm 1 in C square. So it's larger than a plane. And with the standard basis of will be then the vectors ket 0. You did with this ket. Ket 0 is 1, 0, and ket 1 is 0, 1. Now, what happens when we have n qubits? We are not just going to take the normal Cartesian product. We are actually going to take a tensor product. This creates a huge state space. So we take the n iterated tensor product, which is something like that, which is actually going to be c to the power 2 power of n, something huge. And then the computational basic states are the tensor products of the individual basic states. And we can, of course, obtain the other states as linear combinations, with, of course, we must still be of norm 1. And the idea is that, in particular, those that can be expressed as an n-ary tensor, that is just a product of specific states, not necessarily basis state for the individual ones, those are entangled, and they express the particular power of quantum computation. The fact that you can 2 qubits can be entangled and have a non-trivial state. And then how computation works is that pure operations are going to be unitary transformations that are linear or norm-preserving transformations on those states, on that space, which is called an Hilbert space. And so how do we get complex computations? Basically, we start from basic operations, which are unitary transformation called gates. So I just show here 2 basic gates. One is the Hadamard gates, which, if you look at the matrix, maybe you will see that it's a kind of rotation. This is a rotation in a complex, C2, so it's a bit strange kind of things, but it's a rotation. And you have the C0 gate with a conditional note. So it's a connection between 2 qubits. So dependent of the state of the first qubit, we are going to swap the 0 of 1 of the second qubits. So if the first qubit is 0, this is the identity. When you see this at the matrix, if the first qubit is 1, we are going to swap the 2. So this one is swapping the 2 qubits and the value of 0 and 1. Okay. And with this, we can build actually big circuits. One example is Shor's 9-qubit code, which is something that is able to, the idea is you have an encoder part and the decoder part. And if you are going to encode 1 qubit, all the others are set to 0. And then there will be E, which is a possibly noisy quantum channel, which is also encoded as a unitary we can see it as a unitary transformation. And the point is that, and then we have a decoder, and if there is only this is able to correct just 1 error. If there is only 1 error in one of the 9 qubits, this will be able to revert the first one to the correct value. So a quantum circuit is going to apply unitary transformation to input state to an output state. This transformation can span several qubits. So here I have of the first and the fourth, and here the first and the seventh. Or this can be individual one, like the Hadamard gates. And they are applied sequentially. So what's the semantics of this composition? Because what we've seen, the semantics for individual gates were just on a smaller space. And here we're moving to a larger space. So we need a way to apply a gate to a larger space. So for pure computation, the whole circuit can also be described for a matrix. That's the traditional view. And application of a gate then will use a form of padding where you're extending the side of the matrix to adapt it to the whole state. So what we're going to use is taking the tensor product with an identity matrix and then reordering. So here, if we look at the first C0 gate, it's using qubit 1 and 4. So what we are going to do, first we extend, we have 7 extra qubits. So here, all the ones we replaced by actually an identity matrix of size 128 by 128, huge one. And then we need to remember to reorder the second and fourth qubit because we want this one to be there. Okay. So this represents actually another matrix of the same size, 512 by 512, which is doing a tensor permutation, extending second and fourth component of the tensor product. So that would be the transitional way to express that in the semantics. Well, problem with the semantics is that the size of matrices becomes huge. Here we are talking about all the matrices are 512 by 512. And in particular, all the reordering are to be cumbersome. And when we're taking the whole product of all the steps, actually what we get is a completely non-trivial matrix of this side. Okay. Well, of course, people are doing proofs using these semantics. And how do they do that? Well, they will use things like a symbolic representation of the Kronecker products to avoid this blow up of the size of the matrix. And also another approach is to use a labeled direct notations to apply the different gates individually, actually to get things that would commute nicely. But all this actually, in our view, comes at some cost in terms of compositionality. What I mean by compositionality here is that if you look at this code, actually, it's composed of two simpler codes, which is the bit flip code and the signet flip code, and which are themselves able to fix simpler errors in the channel. And you can see that actually this is really a combination of those two on the taking more individually actually to parts of this code, the encoder and decoder parts. We're using the encoder, decoder part of this code, we can build the big one. And we would like to see all these parts as individual gates that we combine. So we want to do everything compositionally. And we want to avoid to be bothered by all the permutations in the middle. So how can we have a nice representation of that allows to represent this circuit in a compact way and then do proofs on that? This is the goal at the end of the day, doing the proofs. Okay. So, well, the first step is that we're going to use a different view on what is our circuit. And we use the isomorphism that C square can be seen as actually a functions of 0 and 1 to C. Okay, simpler. Then the basic states are going to be, well, the state 0 is tech x. If x equals 0, then 1 L0. And if 1 is if x equals 1, then 1 L0. And linear combination of those can provide all the states. Same thing. And the nice thing then is this extends very nicely to n qubits. Then if I have n qubits, this is just 0, 1 to the power of n, which is going to be of the same size. And this one, then we consider the individual state to be just, we take a vector of normal bits. And if the input state x is the expected one, then it's 0. Otherwise, it's 1, else it's 0. So actually, expressed this way, it looks a bit like probabilistic programming, if it were not C but R, which is not too surprising because another actually semantics for quantum programs use this, where you will use actually the norm of the individual, the square of the norms to get a probabilistic semantics. If you include neither amount, you need that semantics. Okay, but then the next step, in order to do what we did to tensor products, the next step will be a generalization when we define the direct power vector space based on this. And what's the idea? Is that rather than going to C, we are going to go to any vector space on a field K. Okay, that's just a big generalization. We generalize also finite type. This was just 0, 1. We could have anything, but this part doesn't matter. You can just fix that the finite type is just 0, 1. And then a basis will be the same thing as present on the previous slides. It's just that here we go back to actually this being just C. If I take K to the 1, actually this is, you can just see it just as the complex. And the interesting part is how are we going to represent our transformations on this? They're linear transformations on that space, okay? T to the power 2 to the power of m. But we want this to apply to any vector space. This will allow to do the nesting. That we had the problem that we needed to do nesting to accommodate for the extra qubits that were not involved in the transformation. We will just hide it under in this T. And so we want this to be a function that works on any vector space. Okay. Problem. How do we answer that functions in this type have a Unix matrix representation that does not depend on T? Because in Coq, actually, you cannot say that in Coq, even though actually this is a parametric representation. Okay. And the answer is that the solution is just to additionally require naturality for this transformation. So naturality is the standard actually category theoretical definition of naturality is that if you bring any linear map, you're going to say that composing G applied to T1 and then the map, or applying first the map and then G applied to D2 is going to be the same computation. This is just standard naturality. I don't go into the details for that. And then this will give us our notion of morphism of unitary transformations are going to be, they are linear, natural, and unitary. If you remember this morning talks by Jeremy Gibbons, this is the same property he had for the deconvolution, except maybe this are not exactly the same definition of linearity and unitarity, even if it's the same naturality. But it's funny that we have the same notions. So here, morphisms just are those linear morphisms that are satisfy identity naturality. A special case is the endomorphism. If I have a matrix, of course, I can produce such a linear transformation that is natural. We can compose those morphisms and still keep the naturality, no problem. And we can define a notion of naturality. We just did the notion of inner product. So a morphism is unitary if it preserves the inner product. That is the idea. So we keep it as an external property because it needs to be proved independently. And if you add the measurement, actually, you end up with things that are not unitary in some cases. So it's important to keep it independent. OK, that was the second step. Let's go to the third step, which is how we really apply those gates, those transformations to the whole circuit. And for this, we will use a notion of length. So the idea is that the length itself is a choice-wise of wires that are going to be connected by the gates. It's a basic combinatorial data. Currying is going to quotient the unused wires away. Here I have a gate that takes, well, 3 inputs in some order, and return them in the same order, okay, and ignores the 2 others. And focusing is going to composing, curry, get, and uncurry to build actually a transformation on the whole system. Okay. So what is a length? A length is just actually an injective function from M to N. So it's just a choice of the wires that we want to use and in which order. That's just what an injective function will give you. And with this, I can define extraction. So if I have a tuple, I can extract a tuple of length n. I can extract m components from it. I can also merge the tuple of length m with a tuple of length n minus m to get a tuples of length n. That allows you to transformation and put things back. I can use the complement of length. In that case, we lose the order because it does not matter if you're talking about the extra wires, we'll just keep them as identity, so we don't care about the order. And we can also, of course, compose lengths. And we come to actually the most important slide in the talk, which is the currying step. which is how along a lens, using a lens, we can change the structure of our quantum state. Basically, the idea is that if I have a quantum state of size of n qubits, I can just decompose it as seeing it direct power m to direct power n minus m to t. Okay, that's the basic idea. This is a natural isomorphism that we have. And then currying is going to be, first I take a state, my n qubits, and I want to decompose just to get m qubits and hide the others under. So it means that I'm taking the state of those m qubits, well, the indices. Here I'm just getting the indices. And then I will get the extra indices. And then I'm going to merge the indices from the both sides along the lens to get how I should access my state. And this will just get the relevant part of the state that I need. And this will get something of the right type if I do it. And inquiry is the opposite operation, where I just get one vector of indices and merge the two vector indices. These two operations form a bijection, and this allows us to change our view of the quantum state. So that we can define focusing. And as I said, focusing is first curry, so that we hide the irrelevant wires below, applied our transformation with the hidden part is of side n minus m here, that part, the part we don't care about, and then uncurry. So this version is going to be linear. We additionally need to prove that it's natural to get a morphism. Okay. What properties do we get on this? Well, we can define composition focus. That is that if I have a composition of morphism applying focus to it, well, this commutes basically. We can also apply focus to a composition of lenses, and we have an important property is that if two lenses are disjoint, we can actually change the order of the operations. And last, for unitarity, if f is a unitary transformation, then focus of f is also a unitary transformation. These are the basic operations we need. Now, last part. I don't know how much time do I have left. A few more minutes. Okay, so last part is how do I use it to prove circuits correct. So first, the big slide at the beginning, the shortcode, I can write it actually this way. This is each individual part is going to be encoded as focus of the morphism version of a matrix. So I have matrices describing the gate for C0, Hadamard. Toffoli is the one, is a C0 with 2 control bits. And I just indicate to which, with a lens, to which parts I want to apply it, to which qubits I'm applying it. So the first one is I have a C0 applied to wire 0 and 1, and then to wire 0 and 2. And the decoder is doing the same thing as the encoder, but additionally, after that, there was a Toffoli gate. If you look back at this circuit, this is exactly the same thing. So these are those two. But additionally, we have this Toffoli gate, which is in the opposite order. Okay. That's what I'm defining here. And then I have this Hadamard. Based on Hadamard, I have 3 Hadamard gates in parallel on wire 0, 1, and 2. So that I can define the string flip encoder and decoder are just the B flip encoder and decoder, but composed with these 3 Hadamard gates. And finally, my encoder is just composing the 3-bit flip encoders on the right, on 0, 1, 2, 3, 4, 5, 6, 7, 8, with 1 6 flip encoder. And decoder will be the symmetrical operation, so I don't write it here. Okay? And then how am I going to build the proof? So the proof is going to be piecewise. That's the point of being compositional. So I prove properties for individual gates, for instance, that C0 applied to 0 and I is 0 and I, and 1 and I is going 1 and flip of I. Well, same thing for Toffoli. If it's 0 and 0, it's going to be the same thing. That Adamar is involutive. That's a well-known property. And for the bit flip, and I can prove that actually. And one interesting one is that bit flip encoder, if it's 1 JK, it will be 1 flip J, flip K, the result. Okay. Then actually the bit flip and sig flip, I can prove that they are going to be equivalent to Toffoli if I am a perfect channel. That is, I just composing the encoder and the decoder without error. I just get a Toffoli gate actually. And finally, I prove that applying the shortcode to I and 8 zeros will be the identity. So the proof is 18 lines in total, and give you just a width of the proof is that using this operation, which has focus DP basis and deep merge DP basis, the idea of the operations is that we are applying focus to a basis vector, and this is equivalent to actually extracting the relevant bit from the basis vector, applying f, and then we do some computation, and later on we have deep merge DP basis. If we are able to return the result of operation to basis vector, then we can just merge back the bits of the basis vector. And if you're not able to go back to the basis vector, it's still okay, because we can, of course, decompose any state in the basis vectors. And at the end, it's the last important slide, but I'm not going to explain the details. But this is half of the proof for the bit flip encoder, which shows that by here the gray ones are applying the tactics. How we can go step by step, starting from the 1 JK to here 1 flip J, flip K. I say that the ultimate result was 1 flip J, flip K, so there will be again the same steps. So the only the tactics are the gray ones. The other ones show you the intermediate states. So that's basically how we do the proofs in this framework. So I move to the conclusion. So we have provided an alternative curve of pure quantum computation that's based on quantum states seen as a function, currying of this function for focusing, parametric polymorphic definition of transformation, and characterizing parametricity by naturality. And this approach allows us to prove a number of pure circuits. So here I've shown 9-qubit code. Also, there is the DHZ state preparation and the reverse circuit. And our conclusion is the ability to manipulate state through currying really seems to simplify at least some proofs. And thank you.
All right, thank you very much, Jacques. And let's maybe have one quick question while Jennifer sets up. All right.
So I didn't understand this. So I thought I understood the story with naturality, but now that you have given a conclusion, I've understood it. So, what is happening with naturality and parametricity? So usually I want naturality. I'm in Coq, so what I do is I ask for the plugin that tells me the parametricity lemma that generates it, and then I get the sort of naturality. But I'm feeling that you do the other direction.
Well, the problem actually, if you we didn't use the plugin for that, and the problem is here that it's actually, if you look here, it's restricted. This one is restricted to the vector spaces, so I don't think that the plugin will give me the naturality in that case.
All right.
So actually, what we do is by hand prove the naturality, and then use it.
All right. Okay. Thanks. Thanks.
Okay. So let's thank Jacques again and have Dennis also talk.
And you have the mic.
Oh, yeah.
Sorry.
Does this sound okay?
Yeah.
Okay.
All right. And if you're ready, Jennifer? Yeah, pretty much. So the last speaker in this session will be Jennifer Pakin, who will tell us how to use model types for the actual quantum programming, I suppose.
Yeah, thank you. So now that we all understand quantum computing very well, I'm keeping things very high level for this talk. So hopefully folks can mostly follow along. But in this talk, I wanted to talk about what I see as one of the core problems in quantum programming language research, which is a trade-off between enabling the sort of high-level, domain-specific programming abstractions that we need for quantum computing, while also preserving properties that are needed to compile that program to quantum devices with very strict resource constraints, which are all of the quantum devices that we currently have and will have for the near future. And so to help manage that trade-off, I'm advocating for the use of modal types, by which I'm referring to the general range of type systems that constrain the way that variables can and can't be used in programs. And so in particular, I'm going to talk about some of the work in progress that I've been investigating as part of the Intel Quantum SDK, which is a C++-based quantum programming framework that is focused on scalability and efficiency for both near-term and far-term devices. But I hope that a lot of these ideas will be applicable to other quantum systems as well. Okay. So what does programming a quantum computer look like? So for the sake of this talk, we should think of a quantum computer as an accelerator, not necessarily used on its own, but used as a component in usually mixed quantum classical algorithms. Classical here is just referring to non-quantum. And so in particular, a programmer will interact with the quantum computer by sending some type of quantum instructions. The quantum computer will execute them and send back probabilistic measurement results in the form of bits or tuples of bits. So today's quantum computers are subject to pretty significant resource constraints. That is partially in terms of the number and connectivity of qubits, the quantum bits available. Things like coherence time, the amount of time that a quantum state will be stable on the quantum computer. And also errors from a variety of physical sources. So quantum computers also operate at near absolute zero temperatures. And as a result, they have very limited access to classical operations. So most of the classical parts of an algorithm have to be performed on a classical computer that is in a place that is maybe relatively close, but is not actually on the quantum device. So the question from a PL standpoint is, well, what are these quantum instructions? And the sort of typical answer today is that these instructions take the form of quantum circuits. These are basically straight line sequences of primitive quantum operations. Those include the unitary transformations that we saw in the last talk, as well as some additional other operations that may be specific to the particular device that you're working on. And so those circuits are either written as a program like this, or they can be described diagrammatically. So to program these circuits, to construct them, many people use circuit generation frameworks, like there's a number of those in Python that are very popular, to explicitly build up those components. And those circuit generation frameworks are very powerful, but they're limited in terms of the expressivity of mixing the classical and quantum algorithms, specifically because these circuit generation frameworks are predicated on the idea that the we're constructing a quantum part, and the classical parts are managed separately in some way. So some relatively concrete examples of this is using classical if statements and for loops to construct these quantum algorithms, as well as things like classical parameters to quantum gates. So there are some quantum gates that take in classical arguments. So the Intel Quantum SDK, which I mentioned, is an attempt to bridge that gap by allowing writing hybrid classical quantum algorithms in an extension of C++. And the extension has a special type of functions. I know this is too small to read, but it has a special type of function called quantum kernels. And all of the quantum operations occur in quantum kernels, but there can also be classical operations inside those quantum kernels. These quantum kernels are compiled to an extension of LLVM with special quantum basic blocks. And the quantum basic blocks are the equivalent of a single quantum circuit, like we saw on the last slide. There's then a runtime system that dynamically dispatches those blocks, gets back measurement results, dispatches new blocks potentially, and so on. Now, the compiler enforces the property that every quantum kernel, which again can contain both classical and quantum operations, gets compiled to at most one invocation of a quantum basic block. So in general, it'll be compiled to some classical preprocessing, some invoking a quantum basic block, and then some classical postprocessing. And so in order to enforce that, it introduces some guidelines that are, written down in plain English that describe how the classical and quantum data can depend on each other inside of quantum kernels. And so here's the summary, but I'm going to focus in on two of them in particular. So the first rule says that all qubit references must be resolvable at compile time. So current quantum devices don't really have a concept of virtual memory, although that's something very interesting to explore. But so all qubit variables have to be mapped to concrete qubit indices by the compiler. So if we want to still be able to work with qubit variables, as one does in the high-level language, they have to be statically resolvable. So this means we can have qubit arrays like this one, as long as the size is known at compile time, and the indices into those arrays are static. What we cannot do is something like this, where we generate a random index at runtime and then use it to index into the qubit array. Okay. So the second rule says that classical parameters to quantum operations cannot depend on measurement results from the same kernel. So to see what that means, let's consider this quantum kernel, which has a single quantum gate, rot x, which is an x rotation, the rot rotation. That argument takes in that gate takes two arguments, a qubit and a classical parameter theta, which is a double or corresponding to a real number. So in this example, the value of theta depends on a C bit or a classical bit C. This is just a simple, conditional, but this kernel is valid because it can be compiled into two parts. So first, we compute the value of theta on the classical device, and then we execute the rotation, the rot x, on the quantum computer, given that value. But in this second example, instead of being passed in as an argument, the C bit C is first written to by a measurement gate. So the measurement gate is doing measurement. That's a quantum operation. And it writes its value to C. So this kernel is actually impossible to compile to a single quantum basic block because the value of theta can't be computed on the quantum device itself, right? So So unfortunately, though, the Intel SDK doesn't currently have a way to check this dependency. So it won't even throw an error, actually. It'll simply behave incorrectly. We just leave it to the programmer to try to avoid this. So, so our goal then is to define some kind of type checker or static analysis pass on the high-level language that enforces the property that every quantum kernel can be compiled to at most 1 QBB. And we want to make sure that the type system is going to enforce all of those English language properties that we saw before. And so to do that, I'm proposing modes. In particular, modes corresponding to so 3 different runtimes that are used in this system. So we have our compile time, we have a classical runtime, and we have a quantum runtime, and the later 2 might go back and forth. So I'll introduce a typing judgment, for now fairly abstract, which says that an expression can be given, is available at mode M, assuming that the variables xi are available at mode M. And to make this more concrete, I'm going to introduce a little toy language of instructions, which has both classical and quantum operations. And the typing judgment, the instructions themselves are all unit typed, but so we just say the instruction is computable at mode M. So to see how this works, let's take a look at a few typing rules. So assignment is fairly straightforward. If both E and X can be are available at mode M, then E can be assigned X. One thing to note is that this is not a binding form. This is assuming X is free in the program. So let's do some quantum operations next. So the rotation gate that we saw before is a special instance of a general unitary, but let's just look at the rotation for this example. So we saw before it takes in 2 arguments, a qubit and, in this case, a real number. So since the qubit variables, we said the qubit arguments all should be resolvable at compile time. So we say that E must have type qubit at mode C, the compile time. And since the real number parameter has to be computed on the classical device potentially, we say that it has to be available at mode R. And if those 2 conditions are satisfied, then the rotation gate can be executed at mode Q at quantum runtime. Okay. So as another example, we have a measurement gate, which also takes 2 arguments, a qubit, which is, again, should be available at compile time, and a C-bit variable. And since the C-bit variable is being written to by this measurement, it must be available at mode Q. Okay, so these rules do, in fact, enforce the guidelines as expected. So for example, let's consider the good function that we saw earlier. In the first case, this function is well typed if the qubit argument is available at compile time and the C-bit argument is available at classical runtime. And in that case, theta is also computed at classical runtime, and this can be used as a parameter in the rotation gate. But in the second example, the C-bit variable is not available at classical runtime. It's available at quantum runtime, right? Because it's being written to by the measurement. So therefore, theta is also only available at quantum runtime, and so can't be used as a parameter in the rotation. Now, since the entire algorithm may involve more than one quantum kernel, we also include something I'm calling invoke, which basically promotes the quantum runtime instructions to the classical runtime. That is, it's invoking a quantum kernel. And when it does so, it also promotes all of the arguments, like this C-bit argument here. And in general, like a modal type, we're going to be scaling all of the modalities in the context by that mode. And we can also go in the other direction, sort of demoting or running instructions from higher modes onto lower ones. according to this preorder. So with that in place, we can talk about the compilation from this sort of high-level language into a lower-level runtime language. And this runtime language is much more strictly separating the classical instructions that are executed on the classical device from the quantum basic blocks that are things that are actually executed on the quantum device. So we go from sort of the intuitive separation between classical and quantum runtime to the actual physical separation between classical and quantum runtime. Some differences is that syntactically in these in all of the quantum operations, the qubit arguments are now specifically qubit identifiers, so natural numbers, for example. And the real number arguments to the unitaries, the xi's, now must be single variables, not arbitrary expressions, because those expressions must have been already resolved by the time we call the QBB. The compilation scheme is type-directed in that expressions at compile time can be evaluated at compile time given lowercase gamma, which maps compile time variables to values. Instructions at classical runtime can be compiled to classical instructions, and instructions at quantum runtime are compiled to a triple. It's the pre-processing classical instruction, the QBB being invoked, and the post-processing classical instruction. As a quick example, because I'm, I think, running low on time, consider our rotation gate. So the qubit argument is going to be, can be computed at compile time, right? It'll evaluate to a concrete qubit address. And then the rotation gate is going to be first doing the quote-unquote pre-processing of assigning E prime to a fresh variable x, and then inside of the QBB doing the rotation with x. As another example, considering sequencing instructions at quantum runtime. So each individual instruction is compiled to a triple, and then these are interleaved. And so the typing judgments should ensure that the dependencies between these components are not violated. So I said this was work in progress. The soundness is, the correctness of this type system is left for future work. But it should look something like this. We need to define an appropriate notion of equivalence between the high-level and low-level languages. If instructions are available at classical runtime and they evaluate to C instruction, then those two should be equivalent. And then for quantum instructions, if they evaluate to a triple, then the instruction should be equivalent to the expected composition. So yeah, so to conclude, I'm talking about the trade-offs between these high-level quantum programming abstractions inside of hybrid quantum classical algorithms, and how can we compile those into to near-term quantum computers that have strict resource constraints. And in this particular case, tracking these three modalities can formalize those previously informal rules. And so thank you all for listening.
Thank you very much, Jennifer, for a very interesting talk. Let's take a couple questions and then break for tea.
Do you have plans to like put this in, if you plan to implement this in the toolchain, then do you plan to expose these modal types to the users, or do you plan to find some way of trying to infer them?
That is a great question. I think that the
because I tried to figure out something like this for another system, and this was something that came up for me.
So we currently already do sort of a lot of this inference, especially of the compile time versus runtime systems. I think the bigger challenge is going to be not I don't want to expose all of these details, but I do want to use them to get useful error messages and integrate that. So I think that's the challenge that I'm anticipating more, but yeah, I think that the inference is also could be quite tricky. Thanks.
I was just wondering, actually, do you mind going back to that slide where you had the example of where it would maybe do something unexpected if you read out a qubit and then use it again in the same block, in the same, like, I forgot the quantum block thing.
This one?
Yeah. So is this because you're reusing the same actual qubit, or like if you had like a second qubit, for instance, that you could use, like can you like read out half of the system and then continue in the same computation without destroying the other half of the system, like something you would need to do maybe in like teleportation or something like that?
So in this system, the problem is not partial measurement, although you do need to make sure that the quantum device allows for that. The problem is trying to do that all in the same quantum basic block. If you stretch it between two quantum basic blocks, at least in our system, then that's fine. Then that does what you're describing, and it even does this. Those two problems aren't distinguished in that way. The reason why this is a problem is because it can't do this intermediary computation, because we've asserted the fact that every quantum kernel should be executable in at most one quantum basic block. And that's for efficiency reasons, so that programmers know how many invocations of quantum basic blocks they're calling.
Oh, okay. So if you have like multiple quantum basic blocks and you have some just ordinary code in between them, it should like maintain the quantum memory between there, right?
Yes, it should, okay. With the caveat that that's more expensive to do that computation in between. And so if your coherence time isn't long enough, then that state's going to decohere.
Okay.
So it's safer to do it all in one quantum basic block if you can. But that is exactly the reason why we try to maintain that invariant that one quantum kernel equals one QBB. Okay. But yes, we do allow you to write down the programs that do arbitrary computation in between quantum kernels while maintaining the quantum state. It's just whether that's actually being maintained coherently or not.
Okay, that's really cool. Thank you.
All right, I think we'll finish the session at this point then, and let's thank Jennifer again. And let's continue the discussions over tea. And 1, 2, okay.
try speaking.
Hello. Hello. Yeah.
Okay, yeah. And you can put it in this pocket.
Okay, let's get started. So welcome everyone to the afternoon session on type-driven runtimes. I'm Ningning Xie. I work for the University of Toronto, and we have 4 exciting talks in this session. And our first talk would be given by Daniel about semantic encapsulation using linking types.
Thank you. So this is joint work with Andrew Wagner and Amal Ahmed at Northeastern. So I guess the first thing I want to address is why are we doing this? Why have we been doing this? We've sort of been banging our head against this problem for a while. And essentially, there's a problem, which is that people come up with all sorts of nice type systems. They come up with really expressive, interesting ways of reasoning about programs, maybe ruling out all sorts of classes of bugs. Maybe they even prove things about those type systems. Maybe they publish papers. And so we end up with all this nice stuff over here. And then if the language actually gets in front of anyone, and anyone starts writing programs in it, it's sort of inevitable that we just punch a big hole in the bottom and say, well, sort of for practical reasons, we need an FFI, or we need to be able to link against C code, or we need some sort of features in order to implement parts of the runtime, or this and that and the other. And this makes sense. Sort of there's an incredible amount of expressive power in these low-level languages. But the problem is that if you stare at this and think about this for a little while, you realize that it means that type checkers, type systems in sort of our flagship examples of type languages are a little bit closer to linters, right? They give us errors, they help us, find bugs, but they only do that to the extent that we're not using these features that sort of render those theorems completely useless, okay? And certain types of programs use more or less of that. And depending on how well tested that code is, right, you can trust it more or less. But that's all sort of, those are a lot of caveats, okay? And so the question really is, can we do better, right? And obviously, I think the answer is yes, and that's what I want to talk about today. Sorry. So the main idea, which is not that clever, it's sort of obvious, is we should model this behavior. We shouldn't ignore it, right? We should say, if we're going to bring in code from C, if we're going to bring in low-level memory manipulation, if that's important, we should actually model this. We shouldn't just pretend it doesn't exist when we actually are proving things. And it's not that people haven't been doing that, right? People have been studying untyped languages. People have been studying effects, state, control effects, all sorts of stuff, basically as long as we've been studying any of this stuff, right? This is very well understood material. The problem is that if you take your nice sound language that has really rich reasoning principles, and then you bring in the semantics of C, and you do that naively, suddenly all your types are the same. Your types sort of have no meaning because C has sort of polluted everything. So the problem is not actually modeling sort of challenging behavior and sort of expressive behavior. The problem is encapsulation. How do you bring in this expressive behavior that you're going to need without sort of letting it destroy everything else, right? And so one observation that drives a lot of this, or maybe how we started making sense of some of it, is that encapsulation, or really that interoperability, happens after some kind of compilation, typically. Okay, and there are ways that this gets more complicated. But basically, if you take a language like OCaml, and I don't mean to pick on OCaml, it's just an example, and C, which I will pick on, there is no sort of OCaml interpreter and C interpreter that model the operational semantics of these two languages, where you bounce between those when you're making foreign calls. It doesn't actually exist, right? We can write it down on paper, but what actually happens is that both get compiled down, and like I said, there are more complicated versions of this picture. This is one of them, right? That they can get compiled down into some common target. There's some place where there actually are calls going back and forth. At some point, control has to switch from a stack of code that came from this language to a stack of code that came from this language, right? At this point, we have some commonality, and this is the point where we're actually bouncing between languages. And so this is the point where we sort of have to at least pay attention a little bit, pay a little bit of focus there. So here's the idea. We should model foreign behavior. So when we import foreign code, we want to give types to that. And so I say novel linking types, not novel as in research novels. Novel as in not in your language already. So the whole idea was you came up with very sort of rich, expressive types that were sound and didn't include maybe low-level memory manipulation. You should give yourself a way of describing that behavior soundly, right? Don't say, well, pointers are kind of like numbers, so we'll just use integers for that, okay? That's not sound, okay? Give yourself accurate types, and then figure out how to encapsulate the code that uses those new types from the rest of the program. So easier said than done, maybe. But this is, if you look at the descriptions look at the documentation in the Haskell FFI or the Camel FFI, this is actually what people describe that you should do, right? Be careful, use these tools sparingly, and then ideally wrap up the nastiness in a safe sort of interface and present that to the rest of the program, right? And like Rust makes this explicit, right? There's an idea, there's a whole language mechanism saying, here's the unsafe part, here's a safe part. Ideally, you only present safe APIs using the safe part. So how can we make this be sort of more explicit so we can make it be more formal? Essentially, first we need actual types. So if this blue language is my core language, then I need to extend the types to somehow express whatever behavior I'm trying to link with. So for example, if I had a pure simply typed lambda calculus with integers as a base type, and I wanted to bring in code that throws exceptions, okay? And there's classic little examples of how this causes weird reentrant behavior if you just allow those functions to flow into the normal types. So we don't want to do that. Instead, we want to split that arrow type into two, okay? Introduce this modality to say, well, there are pure types, that's what we had before, but now there's these weird arrows that might throw exceptions when you call them, okay? We need to connect these new types to our original types. We do this with two typable functions. Lift maps core types to linking types. This is sort of makes real the idea that it is an extension, right? Technically, you might be editing things, adding things, removing things, but we want any existing type to be able to be expressed in this new type system. This is really practically important because I don't want to take any program. If I have any program that type checked, it better still type check, right? Also, I don't want to have to, if you can infer type on this, I'd like to be able to keep using that inference and then just lift it up. Lower is more interesting because this is how we're actually going to implement encapsulation. And so this part on the screen should hopefully look a little suspicious because I'm saying, well, we're just going to take this arrow that can throw exceptions and we'll treat it as a pure arrow. We're actually mapping both functions back to our normal function type. And so the way that we're going to make sense of that is to step back and think about, well, what do we mean by encapsulation? Well, encapsulation has to happen at the level of the target. Okay, so our targets are oftentimes expressive not only in terms of what they can allow you to do, but also what they can allow you to control, right? And so in the case of exceptions, so what I want is for every type, every extended type, I want a little bit of code that I'm writing with these little squiggles that, when wrapped, makes this behave like the lower type. It wraps it up, packages it up, and says, this is now working like encapsulated version. So for exceptions, it just catches them all. It's not complicated, right? This is just it expanded the function, and we run this, and we catch all exceptions. And there's some details, obviously, there. Everything that's on the slides is simplified for the sake of the slides. There are other ways of doing this. This is the dynamic enforcement version. There's a way of doing this statically, where you basically, per expression, have to prove that this expression behaves like that. This is what Rust Belt did. Okay? They showed, oh, this does weird stuff inside, but actually it behaves as this core type. Okay? The reason for presenting this dynamic version is that it allows us to provide this sort of friendly to the programmer interface, which is saying, make explicit the encapsulation boundary. You write in the yellow, the orange language, all the code that involves the FFI, right? It involves making calls, maybe to C or whatever else. And then at some point you say, okay, this is my block that should be safe. So I'd like to be able to use that from the rest of my type system, rest of my language. So wrap it in these boundaries. And then in order for this rule to work, we just insert this in compilation. Okay? Now, I've said that this, I've been gesturing at soundness or how to prove this. If you actually want to do this, most of it relies upon an idea, an old idea, not that old, but Nick Benton was working on, had a series of papers about 15 years ago where he started trying to figure out this realizability idea, which these models, they're logical relations that are inhabited. They're indexed by source types. So in this case, the blue language or the yellow language, but they're inhabited by target terms. So what you're saying is, how do I give meaning to, for example, a Boolean or an integer, source concepts, as these are unary models of sets of target terms. So in my target, maybe I don't have true and false, but I have 0 and 1. I can encode Booleans that way. So that's the meaning of Boolean. Integers are integers. And so this realizability model, we realized, a couple years ago, that this actually becomes really, really useful when you're thinking about interoperability, much more so than it maybe was when Ben was proving soundness of single languages. And the reason why that is that it allows you to ask direct questions about interoperability. Like, is this type in one language or in an extended version of the language the same as in another language? Normally, it's kind of it's a bizarre thing to do unless you've already moved into a model where you have some commonality, right? If you're thinking in terms of the source, the syntax and the operational semantics of the source, these are not really comparable, right? But because the substance of the models are the same, it allows us to do this. And more importantly for this talk, there's a version of this, sort of simplified version of this that answers other questions that we had at PLDI last year. We can ask, what can we put around values from this extended language, the linking code, that make it behave as the core code? How do we actually encapsulate, right? And this is actually sort of sensible to do because all of this stuff is just target code, right? It's all happening in the context of the target. So in particular, we can prove that those lift and lower functions, type level functions, do what they should do, right? For lift to be sound, we want to know that if any value is in the relation, is a value of type, the core type, then it's also a lifted type. That's what we mean by when I said lift must take types to the same type. Right? This is a very formal notion. They are the same. This goes both ways. Okay? They have the exact same meaning. We give meaning to the types by building these models, and then we say these are actually equivalent. Okay? Lower is the more important thing, which is saying if we have an expression, target level expression, that has type, yellow type, then if we wrap this code around it, encapsulation code, it should behave as this core type. Right? Encapsulation should actually do what it's supposed to do. Okay? And this ends up being a little bit trickier if you think about it, because the whole point of having this extended language, in the example that I have for the talk, it can throw exceptions. Okay, so this might throw. This is supposed to catch it, but we're supposed to prove that throwing followed by catching behaves like whatever the resulting type is in this model. Well, this model was intentionally designed without thinking about exceptions. Right? The blue language doesn't know about exceptions. There's not even anything about exceptions. Building models for exceptions, usually there's some kind of continuation relation. There's a lot of stuff about exceptional control flow. How do we take something that does that and prove that that works? Well, it turns out we have to sort of split it into steps where we first show that wrapping it is in the lifted version of that lowered type, because this gives us enough logical structure to actually prove that encapsulation works, because we have whatever additional stuff that possibly exists in these yellow types. And then once we have that, we can use lift soundness to just remove that up arrow. And obviously, all the details of this are in the paper or are in the technical report. A lot of things are simplified here. If you're familiar with logical relation, you're probably confused as to why there is no sort of logical state along with the terms, and that's just for simplified presentation. Once we do that, we have to prove soundness of the whole language. This is completely standard for semantic type soundness. We prove that typing rules imply corresponding implications in terms of the model. What that gives us, once we prove that the libraries we're linking with actually satisfy the types we care about, is an actual soundness proof that includes linking with genuine target code, right, that could not have been expressed in your source language, right? And I have an example here, or I'll show you this first. Sort of wrapping up. We split this, so I said that this was an idea, something that I'd like people to do. I've split this intentionally into sort of two halves. There's an implementation here. There's an idea for an implementation, and then there's an idea for a proof. Okay? The implementation half is what you, if you are implementing a language that has an FFI, could do that I think would actually make things better in terms of programmers being able to reason about things. Okay? That's the first three steps of what I showed you. Right? The most important part here, right, is actually try to engage with what are the features you actually want to bring into your language, right? Rather than just sort of punting on it and say, well, we'll just let in anything from C or anything from assembly or whatever it is. Try to actually figure out what are these features that we don't have in our language that maybe for good reason we don't want to bring in because they make things really hard to reason about. Maybe suddenly your language includes weird modal effects, right? And you don't want actually to put that on most of your programmers. But you can for the people who are actually dealing with sort of writing this low-level code, right? So try to actually figure that out, right? Then define how that weird type system relates to the normal type system, right? And figure out how to actually enforce that, right? These three things are engineering questions, okay? If you do this all right, things are sound and you're good. Obviously, hoping that it works is not usually good enough, or at least we hope you would do better. And that's the point of sort of the second half is how would we actually prove this? And we've given you a recipe for that, which is what these models allow you to do. But the reason for showing it this way is that even if you end up with a proof sketch, you're still in a very different situation than you were than most language implementations are. Because if you prove a language sound in the absence of the FFI, you're not removing a part that is maybe, a detail that is irrelevant. You're removing a part that is incredibly complex, right? Whereas it's possible you could take this language and you could simplify some bits that maybe aren't super relevant, and prove some version of the simplified language, right? And so you don't have a perfect proof, but you have something a lot better than we typically do, okay? So I have an example. I'm going to skip this for time. This is in the paper. We're just one of the case studies that we have. It's a pure functional language, and then it links with a language that brings in state, and it doesn't have polymorphism. So here we're just implementing Fibonacci using a memo table. So we have a way of just writing in values, so it's not exponential. And there's another case study in the paper that brings in exceptions, which is interesting because you get weird control flow and the structures of the models become very different. And both of those compile to an untyped target language, which I think is important to sort of show this doesn't rely upon any types. Sorry. Doesn't rely upon any types at runtime, despite the session that I'm in. It's all done sort of in terms of the actual model, sort of what you, the operations you perform in order to witness the type invariance you want to have rather than anything actually having to happen. So with that, I think I'm out of time. Sorry, I took a little long. Thank you.
Sure. Thank you. It's really cool work. One of the challenges with FFIs is that often it's giving you access to operations that are challenging to encapsulate. In particular, challenging to encapsulate in a high-level type system. And so state can be challenging to encapsulate, but even going further than that, like low-level access to memory or something like that. So can you talk a little bit about how you deal with challenging to encapsulate features?
Yeah, absolutely. So there's a question at the beginning, there's a design question at the beginning, which is this actually something your language should just be able to express natively? Because maybe the answer is yes. Maybe the problem is that your language should be able to express this effect or this feature, right? And then it's a different question, right? And so an example of something that you could not encapsulate if you didn't have it already is, writing to a file. There's not, unless you want to just virtualize the entire file system and be able to roll that back in some weird way. If you allow file writes and reads, there's no way to sort of encapsulate that if you don't have that already, right? And so probably some version of that needs to be in your understanding of how your language works, right? If you want your language to be something someone can reason about. It's if you're trying to do things that actually can be encapsulated, even if it is difficult. And I think memory manipulation is a good example where we do have type systems for low-level memory manipulation, right? This is sort of what a lot of our substructural type systems or what of our separation logics allow us to do is prove complicated things about manipulations of data structures in memory. And the goal always there is to prove that it actually satisfies some API that is safe. Right? That's always the goal, right? And so the idea is, can we actually sort of realize that? And I think Rust Belt is one example of a way to do that. It involves a lot of manual proof, right? You have to prove that, oh, this block of code does what it's supposed to do. But at that point, you're putting a manual proof at the encapsulation boundary, and then you're getting exactly what you want, right?
Right. I'm just thinking about the strategy you described, where we have some encapsulation code that we generated. I'm thinking, how does that work?
I mean, there's dynamic memory isolation techniques that are used as well, like the idea that you would just allocate yourself a block of memory, and then when this is done, If there are no pointers to it, you just throw it away. That's a simplified version of things, right? You could do, sometimes you want to do sort of low-level like arena manipulation, right? And that's something you could express safely, right? If you give yourself that mechanism. I think the question of sort of how do you actually encapsulate is a really fascinating one. It's something that I think especially the security community has been spent a long time working on, and there's lots of really interesting sort of contributions there. And I sort of wish there was a little bit more effort to take some of those features, some of which are in hardware now. You know, people have varying opinions on how nice those abstractions are, but like, can we use some of those to then give us sort of interesting semantic guarantees on the other side?
Yeah, thanks for the discussion. Due to time constraints, let's leave the rest of the discussion as well as any further questions offline. And our next speaker is going to be Peter Seelman, and who is going to tell us about stratified system F.
And try speaking. Test.
Test.
Okay.
Yeah. All right. Well, thank you. Yeah, one fine day, my student Marius and I decided that we wanted to do formalized meta theory for system F. And we also decided by coincidence that we wanted to do that in ACTA. Of course, there's a little problem there. So here I'm showing you actually a formalization of an intrinsically scoped encoding of system F types in ACTA, and it looks all fine. Now, so here we have thrown in a natural numbers type. You have functions, you have type variables, you have a for all type, and well, the encoding is the one that you would expect with types with type variables represented by De Bruijn numbers. That all is very nice. So the unfortunate thing, if you try to model it in ACTA, is that this calculus is actually an impredicative calculus, which means that any quantification that you've got there extends over all types. Or more precisely, if you have a type like this one here, for all alpha.s, then this type variable alpha may range over anything, including the type t itself. And that gives rise to some issues, and in particular it precludes a Sept theoretic semantics, which also precludes that you can model it in ACTA. Fortunately, there's this nice work by Daniel Levent from 1991, I think, where he proposed a predicative fragment of system F, which he called finitely stratified polymorphism, which turns out to be very nicely manageable in ACTA. So in that system, every type really, well, also every polymorphic type, as you will see, has a level, and you can imagine that as a natural number. In fact, in his work, it's a natural number. And then the quantification is restricted so that you can only quantify over types at a lower level. This way, well, the world is nice again. So predicativity, well, if you like predicativity, predicativity is retained, and you have a simple set theoretic semantics if you believe in universes, that is. All right, so if you look at an encoding of the type language, not much really changes. So instead of having this kind of scoped syntax, now you get an intrinsically leveled encoding. So you sort of have a level judgment. So nat is now a type at level 0. If you have function types, well, then the function lives at the least upper bound of the two levels. Type variables, well, they stand for some level, so that should be clear. And all quantification that takes a level that you want to quantify over, and then essentially if the body has type L prime, then your whole type has the type, well, least upper bound of the successor of L right. And that matches exactly, well, that matches the level of a type according to Levon's paper. Well, what turns out to be very fortunate is that it also matches the ideas that ACTA has about encoding universes of sets that are built into ACTA, which means we can actually write down the simple set theoretic semantics just like that. So the only thing is we need to define the meaning of a type variable. So that is, well, if I have a type variable, so that means, well, that's a type variable for something at level L, essentially. So that means, well, if I find some L in delta, so delta is an environment of levels that determines the level for each type variable. So this essentially says alpha is a type variable of level L, and then this gets mapped into set L. So here you see something lurking. I will come back later to that. Right now, let's just take it as granted. If you have that definition, now the meaning of a type is just what you would write down on paper, more or less. Yeah, so the encoding of nat is the natural numbers. The encoding of the function type is the function type. Well, for the type variable, yeah, well, you just look it up, the set in your domain environment, and the for all gets mapped to a for all. Seems easy. Now, it actually took us a week to get to this simple way of writing it, because the trick is that it works only because we are already using level in here in the typing judgment. Yeah, so first we made the mistake of using natural numbers, and then this looks super ugly because you always need to convert between levels and numbers and whatnot, and things get messed up in the way that it's not really palatable to work with it. Yeah, so that was already a nice insight. All right, so now we have the set theoretic semantics. Now we might want to press on. Fortunately, there is some guidance. There is this very nice paper from 2019, System F in ACTA for Fun and Profit, by Chapman and 2 or 3 other people. And they did an encoding for System F omega, which was also using intrinsically typed syntax, which we're also going to use throughout here. And one decision that they made in their development was to use a single environment for type and term variables. So you might do different things, but that's essentially what we're doing. So the first one here, well, empty environment, here you have a type binding that like you would expect. And here you have essentially a level binding that extends the type variables that are currently in scope here. But essentially the structure is the same as in Chapman and Euler. And that means also your variable pointers are not just numbers like here and there. I think they use 0 and successor, but you also have to somehow step over your type abstractions as they get in the way. And the annoying thing is that here you're not getting the type back, but you get the weakened version of the type, so that also causes some headaches in the appropriate places. But once you've got that in place, then you can write down the intrinsically typed expressions very nicely. I left out the part that just deals with the simply typed lambda calculus. You can find that. Well, so if we actually uploaded the paper, you could find that there. Yeah, but here you essentially see for the big lambda, you extend, you take a level as parameter, you extend the domain environment with a level and get a type, and then you just close it with the for all. And here you have type application. And the annoying thing here is that the type here is actually substituting the type argument for the type parameter as you would expect. Yeah, and here if you parameterize over level L, and here the argument in the type application needs to live as level L. Yeah, so that just fits in nicely. All right. I think and now we're actually in place to just write down the set theoretic semantics. And as you can see, it's almost clean. So the first part here, this is just the simply typed lambda calculus. It looks exactly as you would expect. I think everyone well, everyone who has played with Acta has seen that. So these parts are the new parts. So the big lambda is also pleasing. Yeah, so here we are now abstracting over some D at sort set of L, and we can just extend the environment, and that just works very nicely. And here you see the point where things get a bit more nasty, because in order to deal with the with this type application, you cannot easily, well, simply match up the type that is expected at that point with the type that you get out by just type checking this expression here. Yeah, I'll save you the details, but essentially you have to show that the single expression substitution preserves the meaning that we assigned to types. Yeah, so you somehow have to take the meaning of the type argument and stuff it into the domain environment that keeps track of the values of the type variables, so to speak. Yeah, so it's a typical fusion lemma between two maps, essentially. Right, and this is the variable environment that you have to deal with. So essentially, you take the name of a variable and map that into a value of the type of the variable interpreted in the environment that is currently in force. So that works out really nicely. Okay, now let's come back to these set omegas that we saw in a couple of places. So set omega is a sort that has been introduced to Acta because we would also like to speak about types that abstract over levels. In Acta, you can do a level abstraction. You can say for all levels L something blah 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 a set at level L. But these definitions, these functions that are level polymorphic, they also have to live somewhere, and you can't put them in any set L for a specific L. Yeah, so set omega has been introduced, where omega is kind of the first limit ordinal, and well, that you could say, okay, that's a fact given in life. But the annoying thing is that some proofs that show up actually argue about equality at that sort. For example, the single subs preserves that you saw used on the previous slide. Yeah, so essentially this eta here, the variable environment, it's one of those guys, and it also lives in set omega. Yeah, and I said before, yeah, so you need to argue about, well, you have eta and then you extend it and you have to prove some equality about it, which means you need an equality at this level set omega. So the annoying thing is there is a predefined equality, but it's defined parametric over set L. Yeah, so it's defined at every set L, for every L, but it's not defined at set omega. So you have to define it by yourself. So it's really easy, but you get a proliferation of really uninteresting definitions. So you just need to copy library code, and then you need to use it, which means you also need to copy the library functions that depend on it, like congruence and substitution. Equational reasoning doesn't work for these new things, and also it turned out we also needed to use extensionality axioms at these levels. So you also have to write everything, all of that by hand again. Moreover, if you tried the next thing, maybe, well, in Acta you have level polymorphism. Why don't we just extend this calculus with level polymorphism? Now that should be possible to model in Acta as well. Well, yes, you can, but you don't get a simple semantics for types anymore. And the annoying thing is that a level polymorphic, we said that before, is a member of set omega, but it means the semantics of a type can no longer be set omega. Yeah, so an environment can no longer live in set omega. Well, Acta has a way for that. Yeah, so there is the sort set omega 1, which allows you to quantify over things of set omega. So in that you can model it, but you cannot index types by levels anymore. Yeah, but that means if you want to reason at set omega 1, you need more equalities, more lemmas, which are just copies of things that you've had, and so on. Yeah, more extensionality. So the wish to the actor maintainers would be, can't we get some more powerful levels here? Yeah, so actually Levon's 1989 paper, I showed you the 91 paper. There's a paper 2 years before which was called just stratified polymorphism, where he proposes sort of universes with index by ordinals. Well, only up to, I think, omega to the omega, but that seems to be enough. That seems to be a useful subset. Well, I mean, you can't have all levels. That is kind of clearly impossible. There's also recent work in the types 22 proceedings by Besam-Cocon and Dubier and Descardo that might provide some way around that. All right, and I think now I've worked enough on your patience. So the one nice thing that just fell out for free, actually we realized that like 2 weeks ago, all the results that we have here for stratified system F, they apply directly for subsystems, I mean trivial subsystems like ML. Yeah, my students just changed a few lines, restricted the types, and then all the lemmas just go through and you have a soundness proof for ML, more or less. So what do we have as well? Intrinsically typed small step and big step semantics. That's reasonably easy. And you could do that just the same way for full system F. Yeah, stratification doesn't matter here. But then we looked at soundness with respect to the denotational semantics of the operational semantics. So there you need the stratification, because otherwise there's no denotational semantics that you can deal with. And the project that we're currently working on is building logical relations and adequacy, and for that you definitely need stratification. So if you have that, then the logical relation can be defined nicely. Although currently the intrinsically typed syntax sort of strikes back because it requires lots of transfer lemmas in case you I mean, so you saw the subs on the last line of the definition. Well, I can go there. So this stuff here, so this kind of structure explodes in the definitions and also in the proofs. Well, clearly work in progress. If you have any interesting comments and things that we overlooked, I'll be happy to hear about that. And thanks for your attention. I think it should be recorded somehow.
1, 2, 3. All right. So this was awesome. We have a paper on Wednesday. Like, it was just crazy watching this, where we do a very similar development for the same reason, which was we wanted to do something in Agda. Oh crap, we need levels, you know. So I was wondering if you, well, first of all, I'll probably bother you after about that, all the relations there. But did you think about like a decision procedure for stratification as well, or did you begin with the intrinsically typed level representation?
We didn't think about any sort of decision procedures. We just started with the stratified development.
Yeah, because the reason I ask is I tried doing basically indexing it by the AST by NAT and then transform it to level, but NAT is inductive and level is postulate, right? So I could not actually establish this. So. Okay.
Yeah, it gets nasty. I mean, already in the definition of this kind of meaning of types, you need here these substitutions, transfers, and whatnot, and then it gets really impossible to do any proof.
And then the lub leads to all sorts of green goo or whatever it's called.
Yeah, you need to transfer that as well.
Yeah,
you need lemmas already.
Okay. Well, awesome talk. Thank you.
So in the substitution lemma, you've got extensionality in there, right?
I've got that.
You use an extensionality axiom to get this proof?
We are using this dependent extensionality in one proof. I'm not sure if it's this one, but it gets used at some point. Yeah.
Okay. So you can't actually compute. It gets stuck.
Oh. Oh, that's a good question. Well, now I don't know. If it's used in that, you are right. It should get stuck. In which case, would you still accept it as a denotational semantics?
Well, yeah, it's the end of the day. I think we are good.
Okay.
Great. Let's thank the speaker again.
Thank you.
Thanks.
So our next speaker is Frendiof Serbert. Well, sorry for messing up with the name. And he's going to present types as first-class values in the fuzzy language. Please go ahead.
Okay, thank you, Ningning. Frendiof Serbert. I'm actually from Tokiwa Software GmbH, a small company. We're in a small team. We're working on the fusion language. I will give a much more applied talk than what we've heard before. I hope you're fine with that. And I'm actually not a functional guy. I have a very strong object-oriented Java background. So please accept that my vocabulary is maybe sometimes a bit Java-colored, or I still learn a lot in this community, and that's why I'm actually here. So I have four parts in my talk. I assume none of you know about the fusion language, so I'll start with a quick intro into the motivation and basic concepts of the language. And then I focus on different aspects related to types, how types are used as values. I'll introduce something I call type features. And in the end, I want to show how types are used to distinguish, to reference effects. The motivation of the fusion language is to have a very simple language, basically bring different aspects, different concepts down to one concept, which we call a feature. And instead of having the developer make decisions how something is implemented, we want to have tools make these decisions for you. And a third point, we see that more and more systems are safety critical, so we want to have a language, a high-level language that is usable in the safety critical domain. Fusion is statically typed. It has algebraic types. It has parametric types. It supports inheritance and redefinition. It has dynamic binding. And it is a pure language using effects to encapsulate side effects. I'll give some examples, go into details. Here is an example how a product type is defined in Fusion. You define a feature, in this case the feature point, that also defines a product type. The feature point is a constructor that constructs with two arguments, x and y, a product of two float values. A second kind of feature is a function. Here d squared is a function that takes two arguments x and y and computes a result, in this case the distance to the origin of the point x, y. Next, features can be nested, so we can move the d square into the feature point, so it becomes an inner feature of point and has access to the fields x and y in that point. Fusion has immutable fields, so instead of declaring a function, we can also make d square a field which semantically has no effect as long as no side effects occur. The only difference that this has is that it forces the calculation of the value at the point in time where the point is created, while the previous function version calculates the value at the point that d square is called. D square is not the only field in this example. The x and y argument fields are also fields that are implicitly initialized when the point is created. So I'll go back to the function version. What you can do with features to actually execute code is you can perform feature calls, and I give a small example here. You can call a point, you can call this constructor to actually create a value for a point here with the coordinates 3 and 4, and you can call d square on that point, pass the result to another feature, say, which when we run this then prints the result. So fairly simple. Fusion supports different kinds of polymorphism. It has sum types, it has parametric types, and it supports dynamic binding. I will quickly explain that. Going back to our point, I add a second product type, which is a line, and I can now define an object, which is a choice of either a point or a line. So we have a sum type, a tagged union type object here that could be either a point or a line. And we can now define a feature to draw an object and match on the object parameter to distinguish whether it's a point and line, and then draw that. And we can call this draw object with an instance of a point or an instance of a line. And what actually happens is on the call is the instance gets wrapped into a tagged union type. So the point in this example gets equipped with a tag, a type identifier, such that the match in the draw can decide that this is actually a point that wants to be drawn, and correspondingly in the case of a line. The second type of polymorphism is via type parameters. And in this case, first what I need is something called abstract features. So we can define a feature object with an inner feature draw that is declared abstract. If we do something like that, it's very similar to defining an interface in Java or a type class in Haskell. And now we have inheritance, so we can make point inherit from object and provide an implementation for draw. And also line can also inherit from object and provide a different implementation for draw. And now we can have draw object receiving an object with a type parameter t that has to inherit from object and call draw on that. And very similar to the previous example, we can now call draw object with either a point or a line. But what happens here at runtime is slightly different. In this case, the point or line gets not wrapped into some tagged type, but we have monomorphization. That means we get different versions of draw object for points and lines that are used at runtime. Next, dynamic binding is also supported, and for that we need reference type. So we can change our object to be a reference type, which for the parametric type example has no semantic effect at all. The code stays the same, but this now allows us to do something else with that, because reference types can be assigned to from any type that inherits from that. So we can do something like we can define a sequence of objects that contains a mixture of points and lines, and we can iterate that sequence and call draw on these. And what happens now is when we assign these points or lines to that sequence, they get boxed, they can get wrapped into usually heap allocated objects that are equipped with type information similar to the tagged union types. And this type information is then used on a call to decide which version of the draw function should be called. So that much to my quick intro on the Fusion language. Next, I want to use how types are used within Fusion features as values. Coming back to the example with parametric types before that I've shown, where an object O of type T that inherits from an object is called, what I've shown you is actually just a syntactic sugar of the explicit version. Draw object actually has two arguments. It has a T, which is a type that must be object or any subclass of that, and a value argument that is exactly of that type. So each feature that can be called can have a set of type arguments and a set of value arguments. And the type arguments always, by convention, always come first before the value arguments. But syntactically, they are kept as close as possible to the value arguments. Features that define types in Fusion are either constructor features that define product types or choice features that define some types. And all these types may also have type parameters. So we could have a version of point that is not fixed to floating point values, but that has an arbitrary numeric type for the coordinates, or also our object could have an numeric type parameter and then pass it on to the different variants of that choice. When features are called, we provide the type parameters and the value parameters. As an example, I have a pair here. It's a pair of two values of the same type T. And so it has three arguments, the type and the two value arguments for the actual values. And we create three pairs here, one with two integers, one with two strings, and the third one, which is a pair of type option F64, which is a maybe float value. And the first one is nil, and the second is almost pi. And all these calls use all three arguments. Fusion uses a lot of type inference, so in most cases, the type parameters could be omitted. In this example, in the first two cases, the I32 or the string can be inferred from the actual arguments. The third example, values nil and almost pi, are unrelated, so they're in the third example, that the actual type that is desired is an option, cannot be inferred by the compiler, so there we need to explicitly mention the type. In contrast, if we use a type as a feature as a type, like here in a function add, with an argument p, which is a pair of two 32-bit integers, we have to provide all the type parameters. So here we have pair with I32. So if a feature is used as a type, the value arguments are left out and the type parameters are actually presented, are given. So this much to how within calls, types and value arguments are treated in a very similar way. But to make this really powerful, I want to now show how type features can be used in Fusion. As an example, I want to define a feature, a function feature, that sums up all the values in a list, and all these values must be numeric values that we can actually have a defined sum. The problem is we can add the head of the list plus recursively the sum of the tail, but the question is, what do we do with an empty list? Where do we get the values that corresponds to 0 for an arbitrary numeric type. And the solution in Fusion is that the feature numeric defines what we call type features for 0 and 1 that provide a value of the underlying type. And they are declared abstract because in numeric we don't know what the 0 value is right now. And concrete numeric implementations like I32 then provide implementations for 0 and 1 that in this case just returns the 0 or 1 constants. And with this, in our implementation of SUMOF, we can use T.0 to get the value of 0 in the actual numeric type that was given to this feature. And these kind of type features are used a lot within the standard library of Fusion. For example, numeric defines monoids, sum, and product for all numeric values that are based on the 0 and 1 implementation and that use as an operation the plus and times operation as defined for the actual numeric type. And there's an inheritance structure of the type features that is parallel to the inheritance structure of the underlying feature. So numeric defines abstract features like plus or minus that are implemented by concrete implementation, and the corresponding type defines things like 0, 1, sum, and product that are implemented by the concrete type features. So that much to type features. And now I want to come to how types are used in Fusion to refer to effects. I haven't talked about effects yet, so I have to first say how Fusion uses algebraic effects. As an example, I present a hello world here, which uses the IO.out effect. And the syntax we use for that is we use the IO.out as it is installed in the current environment. So we need to be called with an environment where this effect, we could also say capability, is present, that we can print something to IO.out. Then we call this hello world to actually run the code. When this is part of a library function, we have to document that this actually has the side effect, and we do this with an exclamation mark, and the type of the effect that this code uses. And now if we run this, we of course see the output, because IO.out print line prints this to standard out. We can now analyze also our application, and the static analysis determines that this application requires the IO.out effect. There's one thing is special about IO.out is IO.out has a default handler that is installed if there's nothing done explicitly. That's why we don't have to do anything special here. But what we could do is we could run this with a user-defined handler as well, which is what I want to show you now. So we could define our own handler. Don't look at the details here, but what is important is in our own handler, we use io.error to print something, and we mangle around with the string a bit. And now we can create a new instance of the IO.out effect. So we call, in this case, the IO.out effect, providing our implementation of the handler. And now we need to install this to run our code. So we call use on this, which installs that implementation of the IO.out effect and receives a lambda expression that then executes the code. And if we run this, we see our mangled output. What we don't see here is that this is actually not to standard out, but to standard error. And if we analyze the effects on this, we see that actually the whole program no longer depends on I/O out, but now it depends on I/O error, because our handler diverts the output to standard error. Okay. So the last example, which is a bit lengthier, but I hope I can more or less finish in time, is I said that fields in fusion are immutable, but there's a mutate effect that allows us to create mutable variables. So we use this here in a feature that counts the number of elements in a sequence by creating a mutable field, goes through all the elements, increments that mutable field, and returns the result of this counting. And mutate is the type of this effect, so we need to use that type to access that from the environment, and we also need to document that this function requires the mutate effect. Now, to run this, we need to use the mutate effect, and in there we can now use our count, for example, to count the number of even values in between 1 and 10, and it prints 5. Now, it's a bit unfortunate if we want to use a mutable variable locally, that now our whole program becomes dependent on the mutate effect. So we would like to encapsulate the fact that this routine performs mutation somehow. And the way we can do that is we can declare locally a type, I call this MM here, which inherits from mutate. Else it doesn't do anything, doesn't add anything. It's just our own version of mutate that we want to use within this function. And now we install this own version and run our code in there. And we use our version of mutate to create a mutable variable. And once we do that, we no longer depend on the mutate effect, because everything that happens here happens locally. So we have documented that the whole mutation is local to our code, so we can call this count without exposing that there's any mutation of the overall system. But we can go further. We could even make this count, give this count a type parameter, such that the caller can say what is the mutation environment that we are working with. So I call this M, which is a type argument which must inherit from mutate. And now we can use the M here to create our mutable variable. We don't need the code to create the local mutate effect anymore. And but what we need is we need to declare now that our count function depends on the M effect being installed. And we can even now return the mutable value directly, because the caller provides the M and knows what it does. So, coming towards the end. Now, going even one step further, we might want to have the caller provide the mutable variable. So we could even make this a parameter to our count. We no longer need to create this in here. So we can now, as a caller, create our own instance of mutate and pass a mutable variable to our count to be used in that code. That's it. I'm basically through. Ning Ning is getting nervous. So to my conclusion, Fusion, the language aims at unifying concepts, and I think I could show you that types play an integral part in that. One point is that parametric types and value arguments are treated very similarly in function, and types are used to distinguish effects. Thank you.
Thank you. Yeah, thank you for the very nice introduction to this future language. Maybe I will start by asking a question myself. So you introduced all the features supported by this language, but I seem to be missing the high-level picture of this language. What are you using this language for?
Maybe a bit of background. Before I started working on this, I worked for another company where we did an implementation of Java for safety-critical applications. So we saw the need that in safety-critical applications that people want to use higher-level languages, but in retrospect, Java is not the most suitable language for that area. So the idea is to define a simple language for that domain. But I don't have any users at the moment. It's still in a very early prototypical state, so still a lot of And there's a lot of features of that language that I have not mentioned here that are relevant for safety-critical applications.
Yeah, thank you. We can take one question from the audience.
Right. So you mentioned type inference, but there are a lot of things going on here. So what properties do you get from type inference? Do you have principal types, or is it best effort, or what? Yeah. Do you have a disable procedure that always works, or do you sometimes have to put annotations manually?
There's some cases where you have to put the types explicitly, like in the example where from nil and string you cannot infer that you want to have an option of string. These kinds of things. But where it's straightforward, that where basically from arguments passed to a call, you can infer these types, they are inferred automatically.
Okay.
No.
Okay.
So
okay.
It's kind of best effort, but it's in clearly defined cases where the type inference works and where it doesn't.
Right. Thanks.
Yeah, let's thank the speaker again.
Thank you.
You two first.
Do that.
All right, this is the last talk of this session, and Amos Robinson will be telling us about reactive systems in F-star.
Try speaking.
Yep, sounds good.
Yeah, can put it here.
Okay. More safety critical systems. So I'm going to talk about a embedded DSL I've been working on for specifying reactive systems in F-star. Reactive systems. Okay. Reactive systems are computer systems that are in constant interaction with their environment. The classic example is a plane. A plane has flaps and it's got air, and the air changes and it's got to react to the environment. It has very strong, very tight timing requirements. So if it goes wrong, things. Your other reactive systems are motorcycles, trains, cars, robots, also coffee machines. So I'm going to talk about a particular reactive system, which is a driver for a sensor, and it turns out that it turns up in a bunch of these other cases. So let's say we have a driver and we have a thermometer, and we have the display. And the driver says to the thermometer, hey, give me a reading. And the thermometer says, yep, 25 degrees Celsius. And the driver says, okay, update the display to 25 degrees Celsius. Wait a second, and the driver says, all right, give me another reading. And the thermometer goes, nope, I'm dead. At this point, the driver can probably say, okay, we had a reading not long ago. It's probably not too far off 25 degrees Celsius. This will work. And it also tells the thermometer to reset. Wait another second, and the driver asks again, what's the latest temperature? Thermometer says, nope, sorry. At this point, we've run out of, we don't know what the temperature is anymore. So we need to just say, no, it's invalid. If we were implementing this system in the real world, we would probably write it in C, because we want to run it on a microcontroller. We don't want a garbage collector messing with the timing, and we've got to write it in a language we can run. But unfortunately, if we want to verify this system, writing it in C is not very good, right? We've got this, what looks like a sequential program here, but it's actually running concurrently with the driver and the timer and the sensor. So actually specifying this program and verifying it is not trivial. So the idea of approaching verifying these sort of reactive systems is to do the functional programming thing and say, well, instead of reasoning about this imperative mess, we want to lift up the logic to a pure function that we can reason about and just forget about the C code, right? So one way to do this is to implement a function sensor logic, which takes the stream of sensor readings and it returns a stream of statuses and booleans whether to reset the thing. So to call that from our C code, we would need to change our C code a little bit, but because C doesn't support streaming, but we say we implement our streaming function as a init function and a step function, right? And then every step of the C code, it's just going to call this step function and provide it more inputs. It's going to provide it the most recent sensor reading. So this is good because we've gotten our pure system that we can reason about, and we've taken our C code, which was not too complicated before, but difficult to reason about. Now we've got this little stub of C code that is not even worth verifying, right? It's trivial. So if we want to implement our streaming function we could implement it in a language like Lustre or in a synchronous language. So this is what it looks like in a synchronous language embedded in F*. And we say we're describing an age stream. The age stream says at every point in time, if the current sensor reading is valid, then the age is 0. The current sensor reading is good. Otherwise, we want the previous sensor age. That's what this followed by means. But we want the previous age incremented by 1, right? But at the very start of execution, there is no there is no previous age, so we need to provide a default value to start with. So we say valid timeout followed by the age +1. And we do a similar thing for the status. So we can specify this program, right? One of the advantages of writing it in a pure functional language is that we can now specify what the driver should actually do. And one property that it should satisfy is probably that if our sensor logic gives us a reading and it says that this reading that we get is valid, then it should really be a reading that we got from the input, from the sensor itself, right? It shouldn't make up values. And furthermore, it should be a reading in the past. We can make it a little more precise by saying that also it should not be the most recent reading. So this is an okay specification. We can rewrite it as a streaming specification, right? So this is a property that says at all times this property holds. But we can translate that to rather than a property that holds at all points in the stream, we can write it to a stream of Booleans, which should always be true, like a safety property. And we can rewrite the property to say that we'll define the latest valid reading from the sensor's read. And we say if the current sensor reading is valid, we take that value. Otherwise, we take the previous latest reading. Or if there's none, we just take the invalid, right? And now our property says if the status we get from the driver is valid, then the status agrees with our latest reading. So we can prove that this is true. We can prove that this holds of our driver that we wrote. And the way we prove it is by translating to a transition system. One way to prove it is translating to a transition system and then proving it by induction over the trace. And if we translate to a transition system, then we get something like this. It's not, this transition system isn't much different from the program we wrote, except that the transition system isn't as compositional as the streaming program that we write, right? We can take the streaming program and compose them together. All right. So this is a little embedded DSL in F***. It's very simple. It has values and variables and primitive applications. It also has this follow by for delayed streaming primitives, and it has a guarded form of recursion for streaming recursion, and let expressions and assertions for checking things. So we start with an embedded language in F***, and it desugars to a core language, which is intrinsically typed. Then we can translate to a relational transition system, and on that relational transition system, we can prove properties of our system. our core language semantics refines the relational transition system so that anything we prove here holds here. Then we can translate to executable transition systems, which we can actually generate C code for, right? I've proved half of the refinement here, but it's the wrong direction. I mean, it should be equivalence rather than refinement, but I've only proved one direction of the equivalence. So it's a little embedded DSL in F** we can write small programs and verify them and run them on real microcontrollers, which is nice. But at the moment, it doesn't have the support for abstraction is really lacking. I have the start of rely guarantee style contracts so that we can take programs and hide the implementation, but that's not baked yet. In an original implementation, I need common sub-expression elimination because the core language is equational. You can do equational reasoning on the core language, but it's a lot harder to do equational reasoning on the transition systems. So you really want to do common sub-expression elimination before translating to equivalence, before translating to transition systems. However, I originally had an applicative, shallow embedding applicative, where we could use pure functions from F* as worker functions in the language, but then you can't do common sub-expression elimination in F* itself. Yeah, that's all.
Thank you. Any questions from the audience?
All right. So since this is a workshop about types, I noticed that you had. All right. Okay. So since this is a workshop about types, the specification that you're using was a function that returned a stream of bools.
Yep.
Can you make that a stream of types instead?
A
so I
stream
could
of
use type-driven.
Sort of.
Yes.
Yes, good question. I tried and I ran into universe issues, but I can't remember exactly what they were. And for now, I just left it as stream of bools. Bit of a cop-out, but sometimes it's nice to have specifications that we can execute because we can check them at runtime that if we have a specification for how the hardware, like a brake actuator, is supposed to behave, then we can check that that the brake actuator is satisfying its specification at runtime. So restricting it to booleans is in some way nice because it gives you computable.
Cool. Thanks.
We can take one more question.
So when you describe the core language, you said that rec is guarded. So could you tell us more about the type system, clock system maybe you have?
Yep. So latest here refers to latest, but it's guarded by a followed by. So it's a really simple syntactic check. You just check that occurrences of latest only occur inside delays.
So it's a typical Lustre kind of syntactic discipline.
Yep, exactly.
And do you also have clocks in your language, or
no, not yet?
All right. Yeah. So you plan to add this?
Yeah.
And a related question. So what happens if you define nodes? If you use a Lustre language, right? So you don't have functions, you have nodes. Do you do modular compilation or modular verification, or you just flatten out everything? And so like the FBIs, do you compile them at the top level and to just bring all the nodes into one flat namespace and all these FBIs becomes variables there, or do you have local variables?
At the moment, it is all flattened out. I've got contract support, or I'm working on contract support so that we can hide the implementation of nodes. But that's really more for reasoning than code.
Thank you.
Yeah, let's thank the speaker again. Also give another round of applause to all the speakers in this session. And this is the end of this session. Thank you all.
Well, actually, this is also the end of a day of a workshop. So thank you all. It was a fun day. I think I deserve a beer. So in 15 minutes, I will go to a pub nearby. So if you want to join and reminisce about this day or prepare for the next day, you have 6 months to write your next submission to TyDe’24. So get to work, and I guess we can get started in the pub. Okay. So thank you all for today.